Hello there, and welcome to Science for Sleep, where curiosity gets cozy and the biggest questions in the universe take their time. Tonight, we'll be setting out on a journey of imagination and measurement, one that starts right here in the quiet moment of listening and stretches across something almost too vast to fully picture. The central thought is a simple one, but behind it lies an ocean of wonder. How long would it take to cross our galaxy? It's such a straightforward question at first glance, something you could imagine asking at a campfire under the stars or whispering as you stare at a clear night sky. But the answers are not only long and layered, they also touch on physics, astronomy, human dreams, and the way we measure ourselves against the cosmos. Before we set out, I'd love to know, where are you listening from tonight? Is there a window near you with a view of the stars, or perhaps it's the middle of the day and light is pouring in? Do you feel very far from the galaxy, or strangely close to it, as though it were pressing down in the quiet space above? Wherever you are and whatever time it happens to be for you in your part of the world, I'm glad you're here. If you enjoy this kind of slow, thoughtful voyage, a gentle like or a quiet subscription helps this corner reach others who might also be drifting off, learning a little and finding rest. Now, let's take that first step together. The Milky Way, the galaxy we live in, is our home on the largest scales we usually think about. It's not just a blur of light in the night sky, though that's often how we see it with our eyes. It's a collection of hundreds of billions of stars, clouds of gas and dust, planets scattered beyond counting, and structures so enormous that every attempt to describe them ends up sounding like exaggeration. To cross it would be like trying to measure the sea grain by grain of sand, and yet the question remains, how long would it take? To start, we need to know what we mean by crossing. The Milky Way is a disc-shaped galaxy, with a bulging central region and long arms spiralling outward. From edge to edge, the disk spans somewhere around 100,000 light-years, though different measurements give slightly different numbers, sometimes stretching the figure closer to 120,000 light-years, or trimming it back to 90,000. That variation alone is telling. Even measuring the size of our galaxy is no simple matter. We're inside it after all, trying to map the forest while standing beneath the trees. Dust clouds obscure our view, and distances on these scales are difficult to pin down precisely. But let's keep it simple, and use the figure most often quoted, 100,000 light-years across. That number already gives us a starting point. What does 100,000 light-years mean? It means that if you could somehow ride a beam of light travelling at 300,000 kilometers per second, it would still take 100,000 years to go from one edge of the Milky Way to the other. That alone should make us pause. Even the fastest thing in the universe, light itself, the cosmic speed limit, takes a span of time that's 1,000 times longer than all of recorded human history to cross our galaxy. Every civilization that has risen and fallen on Earth, every invention, every war, every work of art, all of it fits inside just a thin sliver of that timescale. To go the full way would be to outlast entire species, entire worlds. But of course, we can't travel at the speed of light. Physics won't allow it for objects with mass. So the question becomes less about absolutes and more about what's possible for us, with our current technology and the dreams we hold for the future. The fastest spacecraft humanity has ever launched is the Parker Solar Probe, moving at speeds of about 700,000 kilometers per hour as it loops around the Sun. That sounds astonishingly quick. It is far faster than any car, plane or rocket we've ever built. Yet even at that pace, to cross the galaxy would take over 600 million years. You could watch continents shift, mountains rise and fall, entire ecosystems appear and vanish, and still the journey wouldn't be close to finished. This contrast between the vastness of the galaxy and the slowness of our machines is humbling. It makes clear that when we talk about crossing the Milky Way, we're really entering the realm of thought experiments, of what-ifs and maybes, rather than practical travel plans. That doesn't make the question any less interesting. In fact, it makes it even more compelling. Because by trying to answer it, we stretch our minds. We confront the scales of time and distance that are part of our universe, even if they never fit comfortably into our daily lives. Imagine for a moment sitting at the window of a spacecraft, looking out not at a planet or a moon, but at the great sprawl of stars ahead. Each one is a sun, some smaller, some larger, many with planets of their own. To cross the galaxy would mean passing near countless billions of them, each with its own story, its own chemistry, its own possibilities. The scale is so large that it's hard not to drift into wonder. And yet the calculation remains. How long? At what speed? With what technology? To begin building answers, we can start with light. 100,000 years is our clean figure if we imagine a photon, a particle of light making the trip. From there, we can slow things down into the realm of human spacecraft. If we take the Voyager 1 probe, which left Earth in 1977 and is still travelling through interstellar space, it moves at about 61,000 kilometers per hour. At that speed, crossing the galaxy would take more than 1.5 billion years. That's a number so vast it's almost hard to treat seriously. The Earth itself is only about 4.5 billion years old. In other words, Voyager 1 would need a third of the entire age of our planet just to cross from one edge of the galaxy to the other. But of course, Voyager isn't trying to do that. It's simply wandering outward, carrying with it a golden record of our species and our music, our voices, our images. Still, it's a useful point of comparison, reminding us of the difference between our ambitions and the scale of the universe. When we shift from actual probes to imagined starships, the numbers can bend a little. Suppose we could reach a speed of 1/10 the speed of light, an enormous leap beyond our technology, but not outside the realm of theoretical physics. At that pace, the crossing would still take 1,000,000 years. If we stretched even further, imagining 1/2 the speed of light, the crossing shrinks to 200,000 years. Faster, yes, but still orders of magnitude longer than any civilization we've ever known has lasted. And this is where the question becomes less about machinery and more about perspective. What does it mean to ask how long it would take to cross the galaxy? For us, bound by human lifespans, it means admitting that no individual could ever make the trip. It would require generations upon generations, whole societies living and dying aboard a ship, never seeing the end, never arriving at the goal, only knowing that their descendants might. That in itself raises fascinating thoughts. How would such a society function? Would the journey become its own purpose, the crossing not a means to an end but a way of life? Would the galaxy become not something to be traversed, but something to be lived within, with each star system a stop along the way? These are the kinds of questions that flow naturally once we begin tugging at the simple thread of how long would it take? And all the while the stars around us shine. The Milky Way isn't just a backdrop for these thoughts, it's an active, dynamic place. Stars are being born, living their lives, and dying in supernova explosions that scatter heavy elements into space. Black holes are pulling matter into spirals of destruction. Clouds of gas are collapsing into new solar systems. In the time it would take for a single crossing, the galaxy itself would have changed. Entire regions would look different, constellations would have shifted beyond recognition, and the very map of the sky would be new. So the question of crossing is not just about travel, it's about time. What does it mean to measure 100,000 years, or 1,000,000, or 1,000,000,000? To cross the galaxy is not simply to go from one side to the other, it's to live through epochs, to watch history on a scale that we usually only assign to geology and evolution. It is to place ourselves not as travellers, but as participants in the story of the cosmos. And as we hold that thought, we can gently turn it over, noticing how it changes shape in the mind. Perhaps the journey is less about reaching the other side, and more about understanding the scale of where we already are. Our galaxy is vast, far beyond any crossing we can achieve, and yet we live within it every day. We orbit a star that is one of billions, in an arm of a spiral that is one of many. We are already inside the crossing, part of the motion, carried along whether we notice it or not. When we start to think about how long it might take to cross a galaxy, the very first obstacle is not speed or technology, but distance itself. We can imagine fast ships, powerful engines, even beams of light carrying us through the darkness. But before we can talk about travel, we have to know what kind of road lies ahead, and in the case of our galaxy, the road is far longer than any path we usually picture. The Milky Way is often described as about 100,000 light-years across. That number gets repeated so often it begins to sound like a fact carved in stone. But the truth is more complicated, because even measuring the size of our own galaxy is a challenge. We live inside it, surrounded by stars, gas, and dust. It's like trying to measure the walls of a forest when all you can see are the trees immediately around you. There are layers of fog, hidden branches, and angles that never quite give you a clear view of the whole shape. Astronomers spend decades refining these measurements, using observations of star clusters, pulsating variables, and radio signals to piece together a map. Depending on which method is used, the Milky Way can appear a little smaller or a little larger, closer to 90,000 light-years across or stretching beyond 120,000. Even now, with space telescopes and sensitive instruments, the numbers carry a margin of uncertainty. Still, 100,000 light-years is a good round figure. It's large enough to capture the immensity of what we're talking about, without drifting into details that only shift by a few thousand here or there. But to truly understand what that means, we need to unpack the phrase light year. People often assume it's a measure of time because of the word year, but in astronomy it's a unit of distance. 1 light year is how far a beam of light travels in a single year, moving at about 300,000 kilometers every second. Over the course of a year, those seconds add up to nearly 10 trillion kilometers. So when we say the galaxy is 100,000 light-years wide, we mean it spans about 1 billion trillion kilometers. That number is so vast it resists meaning. It's hard enough to imagine the distance from Earth to the Sun, about 150 million kilometers, and yet the galaxy dwarfs even that. Sometimes it helps to build comparisons. If Earth were shrunk to the size of a marble, the Sun would be another marble about 15 meters away. On that same scale, the nearest star system, Alpha Centauri, would sit more than 4,000 kilometers away. The galaxy, then, would stretch across distances far larger still, impossible to hold in a single picture, even at such a reduced scale. Thinking in these terms can give us some sense of perspective, though it doesn't fully bridge the gap between imagination and reality. The truth is, our minds are not built to grasp numbers this large in any intuitive way. We can recite them, compare them, even write them out with their long strings of zeros, but to feel them is something else entirely. That difficulty, though, is part of the fascination. The Milky Way is not a small or ordinary backdrop. It's a structure made of hundreds of billions of stars, spread across an expanse so large that even light, the fastest traveller in the universe, needs 100 millennia to move from one side to the other. And that's only the disk. Surrounding the disk is a halo of stars and dark matter that extends even farther, possibly 2 or 3 times as wide. If we include that outer halo, then the distance grows even more intimidating, pushing the crossing into ranges we can barely calculate with simplicity. So when we ask how long it would take to cross the galaxy, we're not asking about a straightforward journey from point A to point B. We're asking about moving across one of the largest structures we can see in the night sky, a structure so vast it takes up most of what we think of as the universe when viewed from our small vantage point on Earth. And just understanding that scale is a journey in itself. Imagine looking up on a clear night. The Milky Way appears as a hazy band of light, stretching from one side of the horizon to the other. To the naked eye, it looks almost like a faint cloud, a pale stripe cutting across the darkness. But through binoculars or a telescope, that haze resolves into countless stars. Each dot of light is a sun, each sun possibly surrounded by worlds. What you're seeing in that stripe is not just a scattering of stars close by, but a view into the heart of the galactic disk, where the density of stars is high enough that they blur together into brightness. That glowing arc is our first clue to the immensity of the galaxy. It's not a few stars clustered together, it's billions upon billions, stretched across tens of thousands of light years. And in that immensity, we live on a small planet orbiting a fairly ordinary star. Our position is about 2/3 of the way from the galactic centre to the outer edge, inside one of the spiral arms called the Orion Arm. From here, the galactic centre is about 27,000 light years away. If we could somehow aim ourselves straight toward it, even light would need 27,000 years to make the trip. That number alone is staggering. It means that when we look toward the centre, the light reaching our eyes left there during the last ice age on Earth, long before recorded history. We're always looking into the past when we look into space, and for our own galaxy, the past stretches farther back than any human memory. The question of distance, then, is not just a matter of numbers, it's also a matter of time. The farther away something is, the older the light we see from it. To cross the galaxy would be not only to move through space, but to traverse history itself, leaving behind the echoes of ancient light and entering regions whose glow may only now be reaching our telescopes. It is a journey measured not only in kilometres, but in centuries and millennia stacked upon each other like layers of sediment. And yet, for all its size, the galaxy is still only one among billions in the observable universe. The Andromeda Galaxy, our nearest large neighbour, is more than 2 million light-years away, dwarfing even the 100,000 light-years of our home. Beyond Andromeda are still more galaxies, clustered in groups, linked into filaments, stretching across cosmic webs that span hundreds of millions of light-years. In this grander context, the Milky Way is not unusually large or small. It is average, a typical spiral galaxy among many. But to us, bound to one planet and one star system, it is everything. Its distances set the stage for our questions. Its scale shapes our perspective. This is why asking how long it would take to cross it is such a human question. It's a way of trying to bring the incomprehensible into our frame of reference. We want to measure it, compare it, put it into terms that connect to our lives. We ask how long it would take because how long is something we understand. We live our days in minutes and hours, our years in seasons, our lives in decades. To put a galaxy into the same language is to try, in some small way, to make it part of us. And perhaps that is why astronomers so often return to metaphors and analogies. Without them, the numbers remain sterile, lists of digits on a page. But with them, we can start to sense what these distances mean. We can say that if our entire solar system was shrunk to the size of a coin, the galaxy would be a disk stretching thousands of kilometres across. Or we can say that if you drove a car at highway speed non-stop, it would take you longer than the age of the universe to cross the galaxy. These comparisons are imperfect, but they bring the enormity down to scales where the human mind can play. Distance is not only the challenge of travel, it is the context in which travel happens. The fact that light takes 100,000 years to move across our galaxy sets the frame for every other calculation. It tells us what's possible, what's not, and what remains forever in the realm of imagination. It reminds us that the stars we see are not neighbours in any ordinary sense. Even the closest ones are separated by chasms so large that our fastest probes would need tens of thousands of years just to reach them. Still, the question remains compelling. How long would it take? Now that we've set the stage with distance, we can begin to think about speed. How fast can we go? And how does that compare to the size of what we face? What happens when we push the limits of physics, or dream of technologies that might let us bend the rules? But before we move towards speed, it's worth pausing again to let the distance itself sink in, to remind ourselves that a galaxy is not a single place, but an expanse so large it resists the very idea of a single journey across it. And in that vastness, we are small, but not lost. We have the ability to ask these questions, to measure, to imagine, and to share the wonder. The distance is beyond us, yet it is also ours, because we live inside it. Every breath we take is taken within the Milky Way. Every sunrise and sunset happens beneath its canopy. We may never cross it, but we are always part of it. And that, in its own way, is enough to keep the thought alive. When people think of the galaxy we live in, many picture the hazy band of stars that stretches across the night sky. That pale strip of light is our first hint of the larger structure we inhabit, though to our eyes it looks flat and cloud-like rather than three-dimensional. In reality, the Milky Way is not a smear in the heavens, but a vast system with a distinct shape, formed by billions of years of gravity pulling stars, gas and dust into patterns. Understanding the shape of our home is one of the first steps in imagining what it would mean to cross it. You cannot talk about travelling across something until you know what that something looks like. The Milky Way is often described as a barred spiral galaxy. That phrase combines two important features. The spiral part refers to the graceful arms that curl outward from the centre, sweeping in long arcs where new stars are born. The barred part refers to the bright, elongated structure that cuts through the middle, a thick bar of stars stretching across the galactic core. Spiral galaxies come in different varieties, some with bars and some without, and the Milky Way happens to fall into the barred category. Astronomers did not know this for certain until the late 20th century, because from our vantage point inside the disk, we cannot easily look at the centre from above. It took careful observations of star motions, infrared surveys that could peer through dust, and radio maps of hydrogen gas to reveal that the middle of our galaxy is not just a round bulge but a barred one. The full structure has several key parts. At the very centre lies a region called the Galactic bulge. This is a densely packed zone of older stars, shaped somewhat like a peanut when viewed from the side, extending above and below the main disk. Within that bulge lies the supermassive black hole known as Sagittarius A, containing about 4 million times the mass of our Sun. Surrounding the bulge is the bar, the elongated collection of stars that channels material inward and likely plays a role in shaping the spiral arms. From the ends of that bar extend the arms themselves. The Milky Way has several spiral arms, though they are not rigid or perfectly defined. They are more like regions of higher density, where stars and gas crowd together in waves. Our solar system lies in a smaller branch called the Orion Arm, tucked between two larger arms named Perseus and Sagittarius. The disk of the galaxy is where most of the visible stars are located, along with nebulae and clusters. It is not very thick compared to its diameter, only about 1,000 light-years from top to bottom in the main star-filled layer. If you picture the galaxy as a giant pancake, the disk is that thin, wide spread of matter. Above and below the disk is the halo, a more spherical region where old stars, globular clusters and dark matter reside. The halo extends far beyond the visible arms, enveloping the galaxy in a vast cocoon. Though we cannot see the dark matter directly, its gravitational pull is measured through the motions of stars, and it accounts for most of the galaxy's mass. When scientists describe the shape of the Milky Way, they often compare it to other galaxies we can see from the outside. The Andromeda Galaxy, our nearest large neighbour, is another barred spiral. Photographs of Andromeda show a bright core, winding arms, and a halo. By studying such galaxies, astronomers can piece together a mental picture of our own. We cannot fly far enough away to take a photograph of the Milky Way's overall shape, but by combining indirect evidence, we can draw maps. These maps change as new data arrives. For example, the European Space Agency's Gaia mission has measured the positions and motions of over 1 billion stars, providing new clarity on the structure. One discovery from Gaia is that the disk of the Milky Way is not perfectly flat. It is warped and twisted, likely due to interactions with nearby galaxies and the uneven distribution of mass. So the pancake analogy, while useful, is not entirely accurate. The disk ripples like a bent plate, a reminder that galaxies are dynamic, living systems rather than rigid objects. Understanding the shape is not just a matter of curiosity, it affects how we think about travel. If one were to imagine a straight line across the galaxy, it would depend on whether you mean through the disk, skimming across the halo, or threading through the arms. Each path encounters different environments. The dense central bulge is crowded with stars, radiation and gravitational forces, while the outer edges are more sparse and quiet. The arms are regions of star formation, filled with bright young stars and nebulae. The spaces between the arms are darker, less populated, though still filled with gas and dust. The halo is diffuse, ancient and ghostly, holding on to relics of the galaxy's past. The shape also tells a story of origin. Spiral galaxies form from clouds of gas that collapse under gravity, flattening into disks as they rotate. Over billions of years, stars form, supernovae explode, material recycles and structures emerge. The bar likely developed as a natural instability in the rotating disk, reshaping the flows of stars and gas. The spiral arms are not permanent fixtures, but density waves, like traffic jams that move around the disk, creating patterns where stars cluster before moving onward. To say the Milky Way has a shape is not to describe something static, but something in constant motion. Every star, including our Sun, orbits the centre, taking hundreds of millions of years to complete one circuit. The arms are not painted lines on a map, but ongoing processes, always forming and reforming. Our solar system is just one small participant in this dance. It lies about 27,000 light-years from the galactic centre, orbiting at a speed of roughly 230 kilometers per second. At that pace, it takes around 230 million years to complete a single orbit. That means during the age of the dinosaurs, Earth was in a very different part of the galaxy than it is today. Over the planet's history, the solar system has made about 20 such orbits, circling the galactic centre again and again, carried along by the shape of our home. When we ask how long it would take to cross the galaxy, the answer depends on what shape we imagine traversing. Crossing through the thin thickness of the disk, top to bottom, would take only about 1,000 light-years, far less than the 100,000 needed to cross the diameter. Still an impossible distance by human standards, but relatively small compared to the full width. Crossing the halo would be larger still, perhaps several 100,000 light-years. Each measure tells a slightly different story, depending on which part of the galaxy you consider to be the boundary. This variation is important, because it reminds us that our home is not a tidy circle with sharp edges. It is a sprawling, irregular system whose boundaries fade gradually. The arms stretch outward and taper. The halo merges into intergalactic space. Even defining where the Milky Way ends and where the next region begins is not simple. The gravitational influence of the galaxy reaches outward, holding on to dwarf galaxies that orbit as satellites, such as the Magellanic Clouds. These companions tug at the Milky Way, distorting its shape and leaving traces of past interactions. In the future, the Milky Way itself will merge with Andromeda, reshaping entirely into a new galaxy. The shape we describe now is only temporary, a snapshot in cosmic time. Thinking about the structure also brings into focus the places we know best. The Orion Arm, our little spur, is not one of the grand main arms. It is a modest feature stretching only a few thousand light-years. Yet within it lies the Sun, Earth, and everything we know. Nearby are familiar constellations, clusters, and nebulae. The Orion Nebula, for example, is a vast star-forming region only about 1/300 light-years away. The Pleiades cluster, a group of young stars, is less than 500 light-years distant. These are close neighbours compared to the full size of the galaxy, but they remind us of the richness contained within even a small section of one arm. To cross the Milky Way would be to pass not only through distances, but through landscapes of stars, each arm with its own character, each region with its own density, colours and histories. If we step back to reflect, the shape of our home is not just a matter of astronomy. It is a context for our lives. Every night we live beneath the disk. Every sunrise and sunset happens in one corner of the Orion Arm. Every thought we have, every dream, every discovery is part of this larger system. To imagine its shape is to realize we belong to something vast and structured, something that has form and order even if it is far too large for us to ever cross. And that realization, while humbling, is also grounding. We know where we live, even if we will never walk its full boundaries. When we try to imagine what it means to cross our galaxy, we almost always begin with the one traveller that has no rival. Light is the fastest thing in the universe, the one benchmark against which all other journeys are measured. Before we talk about spacecraft, generations of humans on board, or technologies that may never leave the drawing board, it helps to picture what light itself accomplishes, because it is the first and most fundamental traveller across space. Light moves at 300,000 kilometers per second in a vacuum. In a single second, a beam of light can circle the Earth more than 7 times. In a minute, it can travel 18 million kilometers. Over the course of a year, those seconds accumulate into nearly 10 trillion kilometers. That distance is what astronomers call a light year. And when we say the Milky Way is 100,000 light years across, what we really mean is that even this tireless traveller racing at the cosmic speed limit would need 100,000 years to get from one edge of our galaxy to the other. To understand how remarkable this is, think about human history. 100,000 years ago, Homo sapiens had only just begun to spread across Africa. Our species had not yet reached every continent. Written language, agriculture, cities, and science were all tens of thousands of years in the future. In other words, if a photon had set out from one side of the galaxy back then, it would only just now be arriving at the other side. The entire span of our recorded history fits inside just a small fraction of a galactic crossing made at the speed of light. When we look at the night sky, we're already seeing the effect of this long travel time. The starlight that reaches our eyes is not current but old, sometimes very old. The sun's light takes about 8 minutes to arrive at Earth. That means when you glance at the sun safely through filters or during a sunset, you're seeing it as it was 8 minutes ago. The nearest star system beyond our own, Alpha Centauri, is a little more than 4 light years away. Its light takes 4 years to reach us. So when you look at it through a telescope, you are looking into the past 4 years ago, seeing the star as it was rather than as it is right now. For stars across the galaxy, the lag can be hundreds or thousands of years. This simple fact changes the way we think about travel. Light doesn't only move across space, it carries information with it. Every star you see is sending you a message that began its journey long before you were born. The galaxy is full of these messengers, each on its way for tens of thousands of years. If you could somehow ride along with one, you would witness a journey longer than the rise and fall of civilizations, longer than the memory of any people. It also tells us why crossing the galaxy is such a daunting task. If even light needs that long, then anything slower becomes essentially unimaginable in the context of human life. The fastest spacecraft we've ever built would take hundreds of millions of years. Even speeds approaching a significant fraction of light still leave us with time spans far longer than our species has existed. The comparison drives home just how large our home really is. When astronomers map the galaxy, they rely on light as their probe. Radio waves, infrared, visible light, and other parts of the electromagnetic spectrum all move at that same universal speed. By collecting them, we build our picture of the Milky Way. In a way, every observation we make is already a kind of journey. Instead of travelling ourselves, we wait for the light to do the work. Telescopes become our ships, photons our explorers. The shape of the arms, the bulge, the halo, all of it is known because light made the crossing first. Think about the central black hole, Sagittarius A. It lies 27,000 light years away. When scientists say they are observing it, what they mean is they are studying light and radio waves that left the region 27,000 years ago, around the time when humans on Earth were still using stone tools. If the black hole suddenly changed in some dramatic way today, we would not know for another 27,000 years. The distance delays the news. Light is fast, but even at its speed, the galaxy is large enough to impose long silences. This delay also applies to the idea of communication across the galaxy. If another civilization exists on the far side, and they were to send us a signal, that message would take 100,000 years to arrive. By the time we answered, another 100,000 years would pass. A full exchange, question and reply, would span 200,000 years. The implication is clear. Communication across a galaxy is not like conversation across a table. It is more like carving words into stone and throwing them into a river that flows for millennia before reaching another shore. The thought of light as the first traveller also leads us to consider relativity. According to Einstein's theory, nothing with mass can reach or exceed the speed of light. It is not just fast, it is the ultimate limit. As you accelerate closer and closer to that speed, your energy requirements rise without bound. Time itself begins to slow relative to an outside observer. The rules of the universe make light the unattainable standard, a ceiling that cannot be broken. That means when we use light as our yardstick, we're really asking about the best-case scenario. No ship, no matter how advanced, can ever quite equal it. And yet, it is worth remembering that even light has its challenges. It moves in straight lines unless bent by gravity. Dust and gas can absorb or scatter it. Over long distances, the clarity of its message can be blurred. The light from distant stars is reddened as it passes through clouds, stretched by the expansion of the universe. So while it is the fastest traveller, it is not invulnerable. Its journey carries the marks of what it has passed through, like footprints on a long road. When we talk about crossing the galaxy then, we often imagine ourselves following the path light takes. If it needs 100,000 years, then anything slower must take longer. But there is also something comforting in this thought. We may never travel those distances, but the light already does. Every night, photons that began their trip long before human history end their journey in our eyes. We are, in a sense, already connected to the entire galaxy, not by travel of our bodies, but by the travel of light. To hold on to this idea is to see the Milky Way differently. It is not just a structure we live inside. It is a web of light in motion, a constant stream of messengers arriving after epic journeys. And as we consider what comes next, how fast we can move, how long our machines take, what limits we face, it helps to remember that light has already shown us the way. It sets the scale, it defines the possible, and it will always arrive first no matter what paths we imagine. When we begin thinking about how long it would take to cross the galaxy, it is easy to leap straight to the grand numbers, light years, millions of years, impossible spans of distance. But sometimes the best way to understand the vastness is to start closer to home, with the journey we are already taking. Every second of every day, we're moving beside the sun as it travels through the galaxy. Our planet is not fixed in space. It is part of a system that orbits the centre of the Milky Way. In a very real sense, we are already passengers on a long voyage, one that has been underway since Earth first formed more than 4 billion years ago. The Sun, like every other star in the galaxy, follows a path shaped by gravity. The central mass of the Milky Way pulls on it, and the collective influence of billions of stars, dark matter and gas defines its motion. At this moment, the Sun is about 27,000 light-years from the centre. It moves around that centre at roughly 230 kilometers per second, or about 800,000 kilometers per hour. To us on Earth, those speeds are invisible. We don't feel the motion. The night sky appears calm, the constellations fixed. But over longer timescales, the Sun's movement becomes clear. Stars shift their positions relative to one another. Constellations slowly change shape. The solar system as a whole traces a vast orbit around the heart of the galaxy. That orbit is not quick. At its current speed, the Sun takes around 230 million years to complete a single revolution. In other words, the last time the solar system was in its current position in the galaxy, the Earth looked entirely different. It was the middle of the Triassic period, long before the first dinosaurs had evolved. Mammals did not exist. Flowering plants had not yet appeared. The continents were fused into the supercontinent Pangaea. Since then, the solar system has made only about 20 trips around the galactic centre. Each lap is so long that it outlasts entire geological eras on Earth. Thinking about this orbit helps put our place in perspective. When we ask how long it would take to cross the galaxy, we might imagine building a ship and charting a course. But in another sense, we're already on that course. Our star is carrying us along a path that we cannot steer or stop. We are walking beside the sun, though the word walking hardly captures the velocity. We are being swept around on a path that will eventually bring us through different arms, past different clusters, under skies that will slowly shift. The galaxy is not static, and neither are we. As the sun orbits, it does not follow a perfectly circular track. Its path wobbles slightly, moving up and down through the galactic plane. About every 30 million years or so, the solar system drifts above or below the midline of the disk. This motion may influence the environment of Earth in subtle ways. Some scientists have proposed links between these oscillations and cycles in biodiversity or climate, though the evidence is still debated. Regardless of any specific connections, the fact remains that we are not simply circling the centre in a flat loop. We are weaving through a three-dimensional landscape carried by the sun's motion. One way to picture this journey is to scale it down. Imagine the galaxy as a city 100 kilometers across. On that scale, the solar system would be a tiny car driving around the outskirts at a steady speed. It would take the car hundreds of thousands of years to circle the city once. From the perspective of someone sitting inside, the trip would feel endless, the buildings along the road changing only slowly. This metaphor is crude, but it helps illustrate the central point. We live in a system where even ordinary motion, the background drift of a star, operates on timescales that dwarf human experience. The sun's orbit also reminds us that the galaxy is not empty. Along the way, we pass through regions of varying density. Sometimes the solar system comes closer to spiral arms, where star formation is more active. Sometimes it drifts into quieter inter-arm regions, where fewer young stars shine. Over millions of years, these changes may affect the amount of cosmic radiation Earth receives, or the frequency with which we encounter passing clouds of gas. It is possible that such galactic weather has subtle influences on our planet's history. As passengers of the sun's journey, we are shielded by its magnetic field, which extends outward in a bubble called the heliosphere. The heliosphere acts as a protective cocoon, deflecting some of the charged particles that stream through the galaxy. As the solar system moves, the shape of the heliosphere shifts, responding to the conditions of the interstellar medium it passes through. In a sense, the sun is like a ship ploughing through a sea of particles, and Earth is a cabin inside that ship. We may not notice the motion, but it defines the environment we live in. Another way to think about walking beside the sun is to consider the distances it covers. At 230 kilometers per second, in a single year the sun travels more than 7 billion kilometers relative to the galactic center. Over the course of a human lifetime, that adds up to trillions of kilometers. None of us will live to see even a fraction of a percent of the sun's full orbit, but we each ride along for a short stretch. Our lives are chapters inside a voyage that has been underway for billions of years and will continue for billions more. This perspective changes how we think about crossing the galaxy. We often imagine it as a future endeavour, something we might attempt with advanced technology. But the truth is, the crossing is already happening. We are already in motion, already covering ground. It is simply that the scales are so large and our lives so brief that we do not notice the progress. From our point of view, the stars are steady. From the galaxy's point of view, we are part of a restless current, flowing outward and around. It is also worth noting that the sun's path is influenced by encounters with other stars and masses of dark matter. The orbit is not fixed forever. Over long timescales, gravitational nudges alter its course. The galaxy is not a smooth, empty disk, but a crowded environment. Stars pass near each other, clusters disperse, clouds of gas move. Each interaction leaves small imprints on the paths of stars. So even though we talk about the Sun's orbit as though it is a clean circle taking 230 million years, in reality it is more like a winding route, gently perturbed again and again. When we ask how long it would take to cross the galaxy, we might imagine drawing a straight line from one side to the other. But stars like the Sun show us that there is no straight line in practice. The paths are curved, bent by gravity, shaped by interactions. Walking beside the Sun means following a route that is defined by the collective pull of everything around us. It is not a straight highway, but a winding trail, and we move along it whether we choose to or not. This motion is also our connection to the rest of the galaxy. When astronomers measure the Milky Way's rotation curve, they are essentially measuring how stars like the Sun move around the centre. Those measurements reveal that stars far from the centre move faster than expected, evidence for the presence of dark matter. In this way, our Sun's orbit is not just a background fact. It is part of the key data that helped reveal the hidden mass of the universe. Walking beside the Sun is not only a poetic idea, but a scientific observation. Our journey provides evidence about the structure of the cosmos. So when we think about crossing the galaxy, perhaps we should start here, with the journey we're already on. The Sun is our ship. The Earth is a cabin on board. Every day we ride along as it carves its immense path around the centre of the Milky Way. We may dream of faster ships, of engines that could shorten the trip. But in truth, we're already part of a voyage larger than any human plan. The Sun has been walking this road for billions of years, and it will continue long after we are gone. To imagine crossing the galaxy is to imagine something grand and future-bound. To recognise that we are already walking beside the Sun is to see that the crossing has already begun. When we think about crossing the galaxy, our minds almost immediately turn to speed. And if we imagine the ultimate in speed, we arrive at the same place every time, the speed of light. It is the fastest traveller allowed by the universe, the benchmark against which every other attempt at motion must be compared. To talk about riding on beams of light is to imagine what happens if we could somehow join that flow, to consider what it would mean to see the galaxy as photons do, to cover ground in the most direct way nature permits. The speed of light is about 300,000 kilometers per second. In human terms, it is so fast that ordinary scales become useless. Light can travel from Earth to the Moon in just over 1 second. It can cross the orbit of Earth around the Sun in about 8 minutes. To reach Pluto takes about 5.5 hours. To reach the nearest star system, Alpha Centauri, takes a little more than 4 years. These numbers, though still manageable, already begin to drift outside human lifetimes. Once we extend to larger scales, the timescales quickly become enormous. Crossing the galaxy at this maximum possible pace still takes 100,000 years. If you were to imagine yourself somehow attached to a photon, the picture grows even stranger. According to Einstein's theory of relativity, from the perspective of light itself, no time passes at all. A photon leaves a star and arrives at its destination without experiencing the journey. For the photon, emission and absorption happen in the same instant. But for us, standing at rest or moving only slowly by comparison, the journey stretches across tens of thousands of years. Riding on beams of light is therefore not just a thought experiment about speed, it is also a thought experiment about time. To move at that pace is to remove yourself from the flow of time as we know it. This is where relativity reshapes our imagination. The closer an object with mass gets to the speed of light, the more its time slows relative to an outside observer. Its mass effectively increases, requiring more and more energy to keep accelerating. At the speed of light itself, those requirements become infinite. That is why no particle with mass can ever achieve it. Light remains a unique case, massless, and therefore able to travel at that ultimate limit. So when we picture riding on beams of light, we are really picturing something that cannot happen for us, but that does happen constantly for photons all around us. Every second, light is leaving stars, crossing space, and arriving at new destinations, carrying with it information about where it came from. Consider what this means for the stars we see. When you look up at the night sky, you are looking at light that has been riding toward you for years, centuries, or millennia. Each photon has been in motion all that time, unaffected by age, carrying its message until it reaches your eye. If we could truly ride along, the galaxy would become a compressed landscape. Every distance collapsed into an instant. What we see as immense journeys would vanish into immediacy. For astronomers, this property of light is the foundation of their work. Telescopes are, in essence, devices that collect photons. Every image is a record of light that began its trip long ago. In this way, beams of light are already our explorers. They ride across the galaxy without ships, without fuel, without pause. They move from star to star, from cloud to cloud, eventually reaching Earth where we interpret them. Riding on beams of light, in the sense of following what they reveal, is something we already do every day. If we imagine building technology that could move us at even a fraction of that speed, the timescales shift dramatically. At 10% the speed of light, a journey across the galaxy would take 1,000,000 years. At half the speed, it would still take 200,000 years. Even these reduced timescales remain enormous compared to human civilization, but they are much smaller than the span of the galaxy as measured in light years. This contrast shows how powerful the benchmark of light is. It sets the ultimate floor on travel time, a figure no amount of technology can undercut. It also shows why so many concepts in science fiction revolve around light speed. Characters in stories may speak of warp drives, hyperspace, or wormholes, but the common thread is always the same, an attempt to overcome the barrier of light speed. Because until that barrier is addressed, the idea of crossing the galaxy remains impractical. Light shows us what is possible, but also what is forbidden. To make the idea clearer, let's walk through some comparisons. Imagine a spaceship that could travel at the speed of the Parker Solar Probe, currently the fastest human-made object, moving at about 700,000 kilometers per hour. At that pace, to cross the galaxy would take more than 600 million years. Now imagine upgrading that ship to 1/10 the speed of light. The journey shortens to about 1,000,000 years. Push it to half the speed of light and it drops to 200,000 years. At the full speed of light, the journey takes 100,000 years. The progression is stark. The closer you approach the speed of light, the more the galaxy begins to look crossable, though always at timescales longer than human lives. But the idea of riding on beams of light also has another layer, one connected to energy. To accelerate even a small object to near light speed requires colossal amounts of energy. The faster you go, the harder it gets. This is why practical discussions of interstellar travel often focus on propulsion methods that use light itself. Concepts like solar sails or laser propulsion rely on harnessing photons to push a craft forward. In these designs, the craft is not riding on beams of light metaphorically. It is literally being carried by their momentum, pushed across the void by streams of photons. Though no such craft has yet been built for a full-scale interstellar journey, experiments with small prototypes are underway. Projects such as Breakthrough Starshot envision tiny probes accelerated to a fraction of light speed by powerful ground-based lasers. If successful, they could reach nearby stars within decades rather than millennia. Even here, though, the galaxy as a whole remains daunting. A probe moving at 1/5 the speed of light would still need 500,000 years to cross. The numbers remind us that while light is fast, distances are vast, and the combination keeps the dream of galactic crossings firmly in the realm of imagination. Still, there is something profound about thinking in these terms. To picture ourselves riding on beams of light is to step outside our usual scale. We live our lives in minutes and hours, counting days and years. Light ignores these divisions, leaping across the solar system in minutes, across the galaxy in millennia, across the universe in billions of years. It is the universal traveller, moving always at the same pace, unaffected by who is watching. By imagining ourselves alongside it, we gain perspective. We see our own slowness, our own limits, but also our connection to the cosmos. Because light does more than move, it illuminates. Every detail we know about the galaxy, from the shape of its arms to the presence of its black hole, comes from light. By collecting it, by riding along in thought, we turn photons into knowledge. And that knowledge, though it may never shorten the journey, brings the galaxy closer in a different sense. So as we continue to wonder how long it would take to cross our galaxy, it is worth holding on to the image of beams of light already making that trip. They leave stars, travel across the void, and eventually reach us. We may never ride them in reality, but in a way, we already do. Every time we look up, every time a telescope collects a faint signal, every time starlight falls onto Earth after a journey of thousands of years. The galaxy is immense, but beams of light are always in motion, always crossing, always arriving, and in their journeys, we find both the limits and the possibilities of our own. When we step away from the beams of light and look back at the machines we have actually built, the contrast is striking. Light is the ultimate traveller, the benchmark that defines the fastest possible speed. But our spacecraft, the real ships humanity has placed into the void, move at a very different pace. Compared to photons, they are crawling. And yet, for us, they represent the pinnacle of engineering, the clearest evidence of our ability to reach beyond Earth. To understand how long it would take to cross the galaxy, we cannot skip over this reality. We must reckon with the slow march of spacecraft. The fastest human-made object so far is the Parker Solar Probe. Launched in 2018, it was designed to study the outer layers of the Sun's atmosphere. To get close, it had to dive deep into the Sun's gravity well, and in doing so, it was accelerated to speeds greater than any spacecraft before it. At its peak, the Parker Solar Probe moves at about 700,000 kilometers per hour. That is nearly 200 kilometers every second, an extraordinary velocity by human standards. In that time, it could travel from New York to Los Angeles in less than 20 seconds. To us, it is unimaginably fast, and yet, in galactic terms, it is almost motionless. At 700,000 kilometers per hour, to cross the Milky Way's diameter of 100,000 light-years would take more than 600 million years. That figure is so large it overshadows almost everything else we know. For context, the age of the dinosaurs ended 65 million years ago. Multiply that by nearly 10, and you still have not reached the time needed for a single crossing at Parker Solar Probe speed. The Earth itself is only about 4.5 billion years old, which means a crossing at that pace would consume a significant fraction of the entire lifetime of our planet. Consider another example, Voyager 1. Launched in 1977, it has now travelled beyond the heliosphere into interstellar space. It is moving at around 61,000 kilometers per hour relative to the Sun. This is far slower than the Parker Solar Probe, but it remains one of the fastest spacecraft ever built, and it holds the record for the farthest distance from Earth achieved by a human-made object. At Voyager 1 speed, the time to cross the galaxy would stretch into 1.5 billion years. That number is even more difficult to imagine. It means that if Voyager 1 had been launched at the dawn of Earth itself, it would still be far from completing its journey across the Milky Way today. When we frame things this way, the slow march of spacecraft becomes unavoidable. Our machines are remarkable achievements, but they operate on scales that make galactic crossings functionally impossible. We send them to nearby planets, to the outer reaches of the solar system, and in the case of the Voyagers, into the space between stars. But none of them are designed for journeys across the galaxy. Their lifespans are measured in decades, their power sources limited, their speeds tiny compared to what is required. This reality does not make them less impressive. Voyager 1 and 2 carry golden records, phonograph discs with sounds and images of Earth. They are small messages in bottles cast into the ocean of space. If an alien civilization were to encounter one, it would find a compressed time capsule of humanity in the late 20th century. But those bottles drift slowly. In the time it takes Voyager 1 to move a single light year, thousands of years will pass on Earth. That is the slow march of spacecraft. Why are they so slow? The answer comes down to energy. Reaching high speeds requires enormous amounts of energy, and rockets are limited in how much fuel they can carry and how efficiently they can burn it. The Parker Solar Probe reached its record speed not by firing engines endlessly, but by using the sun's gravity to accelerate as it fell closer and closer. Voyager 1 used gravity assist from Jupiter and Saturn to slingshot outward at higher speeds than rockets alone could provide. These methods allow us to cheat a little, using celestial mechanics to gain velocity, but they still fall far short of the pace needed to traverse the galaxy in meaningful timeframes. Another limitation is endurance. Even if a spacecraft could be accelerated to higher speeds, it would need to survive for hundreds of thousands or millions of years to complete the journey. Electronics degrade, power sources run out, collisions with tiny particles of dust at high velocity could be catastrophic. The galaxy is not empty, and travelling at a fraction of light speed through interstellar space poses dangers that are trivial at slower speeds but deadly when scaled up. Our spacecraft are not built for those conditions. They are designed for missions lasting decades at most, not geological ages, and yet the slow march is instructive. It shows us the difference between imagination and engineering. On one side, we picture beams of light, photons racing across the galaxy in 100,000 years. On the other, we look at our actual machines, crawling so slowly that billions of years would not suffice. The gap between these extremes is the gap between what physics allows in principle and what technology permits in practice. To cross that gap, we would need breakthroughs far beyond what we currently know. But it also shows us something hopeful. Each spacecraft we launch is faster and more ambitious than the ones before. The Parker Solar Probe is faster than Voyager, which was faster than the missions before it. Future projects may push speeds higher still. Concepts like nuclear propulsion, fusion drives, or solar sails could, in theory, accelerate craft to significant fractions of light speed. They remain speculative, but they represent steps toward narrowing the gap. The march may be slow now, but it is not motionless. This slow march also gives us perspective on time. We often think of human history as long, stretching back thousands of years. But against the backdrop of galactic travel times, it is an instant. The spacecraft we have launched so far will not cross the galaxy. They will not even cross a significant fraction of it. But they do represent the first footsteps, the first attempts to move beyond our immediate neighbourhood. They are small, but they matter, because they show that motion is possible. Consider the golden records again. They carry greetings in dozens of languages, music from cultures around the world, sounds of nature, and images of life on Earth. They are not meant to be practical tools of communication. They are symbolic, a way of saying that humanity was here, that we looked outward, that we wondered. The spacecraft carrying them may be slow, but their very existence tells us that we are capable of thinking beyond our planet, beyond our lifetimes, beyond even our galaxy. If the slow march continues, if each generation builds faster ships, then eventually the pace could increase. Perhaps not to light speed, but to fractions of it. At that point, the galaxy would still take hundreds of thousands of years to cross, but the dream would come closer to reality. The slow march, then, is not only a description of spacecraft moving through space, it is a description of humanity's progress step by step, experiment by experiment, moving from the possible to the previously impossible. For now, though, the numbers remain fixed. Parker Solar Probe, 600 million years. Voyager 1, 1.5 billion years. Other probes, even slower. These are the scales of time we're dealing with when we talk about actual machines we've launched. It is sobering, but also motivating, because it shows us how far we have to go and how much room there is for discovery. If light is too fast to reach and our current probes are too slow, what lies in between? What technologies could bridge the gap? What new methods of propulsion might turn the slow march into something quicker, if not immediate? Whenever the subject of crossing the galaxy comes up, sooner or later the conversation turns toward limits. We can imagine faster spacecraft, stronger engines, and future breakthroughs, but there is one boundary in nature that refuses to budge. That is the speed of light. Physics tells us that nothing with mass can move faster than light through space. This restriction is not just a technical problem waiting to be solved. It is a fundamental feature of the universe. Understanding it is crucial if we want to know what crossing the Milky Way really means, because this speed limit sets the outer boundary for every possible journey. The number itself is straightforward, about 300,000 kilometers per second. In 1 second, a beam of light can go around Earth 7 times. In a minute, it can travel 18 million kilometers. In a year, nearly 10 trillion. These figures define the light year, the distance light covers in 12 months. When astronomers say the galaxy is 100,000 light years across, they are saying it is 100,000 times that distance. That is already staggering. But the real challenge lies not in the size of the number, but in the impossibility of exceeding it. Einstein's theory of relativity explains why. As an object with mass accelerates closer to the speed of light, its energy requirements grow. The faster it goes, the more energy it takes to increase its speed even slightly. At everyday velocities, this effect is invisible. Cars, planes, even rockets move so slowly compared to light that relativity barely matters. But at a significant fraction of light speed, the effect becomes dominant. To reach 90% of light speed would require enormous amounts of energy. To reach 99.9%, the demand skyrockets. And to actually reach the speed of light itself would require infinite energy, a physical impossibility. That is why the speed of light is not just very fast, but the ultimate barrier. This is not merely a mathematical trick. It has been confirmed again and again in experiments. Particles in accelerators, such as those at CERN, can be pushed to speeds very close to light. They circle tunnels at 99.999% of that speed. But no matter how much energy is added, they never reach 100%. The universe simply does not allow it. Photons, being massless, are the only things that can travel at that exact pace. Everything else must remain below it. For galactic travel, this restriction carries enormous implications. Even if we built engines capable of pushing ships to incredible velocities, we could never match the pace of light. We could get close, but not all the way. That means that the lower bound on a galactic crossing is set in stone. 100,000 years is the absolute minimum, and that is for a traveller that has no mass at all. For us, with mass and limited energy, the trip would always take longer. This limit also brings time into the conversation in strange ways. As an object approaches light speed, time dilation occurs. From the perspective of an outside observer, the traveller's clock ticks more slowly. A ship moving at 90% of light speed might experience only half the time that passes for someone at rest. At 99.9%, the difference is even more dramatic. For the crew on board, the trip might feel shorter, though from the outside, centuries or millennia still pass. This creates curious scenarios where, in theory, humans could reach distant stars within their lifetimes by travelling very close to light speed, but when they arrived, vast ages would have passed on Earth. Relativity allows for journeys to feel short for the traveller, while remaining long for everyone else. This feature of time dilation is often described as a loophole, but it does not break the rule. The speed of a light remains uncrossable. The effect simply shifts the way time is experienced. For crossing the galaxy, it means that any realistic ship would still take far longer than a human lifespan in the eyes of Earth, even if the passengers themselves felt otherwise. This tension between outside time and inside time is part of what makes the subject so fascinating. The speed limit of the universe is not only about travel, it also governs communication. No message can move faster than light. Radio signals, laser beams, and any other form of electromagnetic transmission all obey the same law. That means the fastest way to send information across the galaxy still takes 100,000 years from edge to edge. This alone explains why interstellar communication is so challenging. If another civilization exists far away, we would be speaking to one another across gulfs of time measured in millennia. A single exchange would take longer than the rise and fall of human civilizations. It is worth reflecting on how radical this is compared to our daily experience. On Earth, the idea of a speed limit is familiar. Cars have speed limits on roads, airplanes have practical limits based on aerodynamics, rockets have constraints based on fuel. But in principle, you can imagine overcoming those by changing the technology. A better engine, a stronger design, and the limit is broken. With light, that is not the case. No technology can ever overcome it. It is not a practical obstacle, but a fundamental one. The laws of nature themselves forbid faster travel. This fact has led to a great deal of speculation. Science fiction often imagines ways around the speed limit. Concepts like warp drives, wormholes, or hyperspace are attempts to cheat the rule, to create shortcuts that do not technically exceed light speed but bypass the distance in some other way. Physicists have studied some of these ideas seriously, such as the Alcubierre warp drive, which involves compressing space in front of a ship and expanding it behind. In principle, this could allow effective faster-than-light travel without breaking relativity, because the ship itself would remain stationary relative to its bubble of space. But the energy requirements for such a device are enormous, far beyond anything we can imagine producing. Wormholes, another speculative concept, would connect distant points in space through tunnels. Again, the mathematics allows it, but the practicalities are overwhelming. For now, these remain ideas rather than possibilities, so the speed limit remains intact. We live in a universe where light defines the fastest possible pace. That boundary shapes every question we ask about galactic travel. Without it, the journey would be a matter of building better engines. With it, the journey becomes a matter of rethinking what is possible. At the same time, this limit gives us stability. If signals could outrun light, causality itself would break down. Events could be influenced by future events. The order of cause and effect could be scrambled. The speed limit preserves the consistency of time. It keeps the universe orderly. In that sense, it is not just a barrier, but a framework that makes physics work. The fact that nothing outruns light is the reason everything else makes sense. For our purposes, though, it means humility. When we imagine crossing the galaxy, we must remember that the fastest possible traveller still requires 100,000 years. Every spacecraft we build, every propulsion system we dream up must exist within that frame. The speed limit of the universe is not a suggestion, it is the law. And yet, even with this constraint, there is still room for wonder. Time dilation offers strange possibilities. Theoretical propulsion concepts might one day approach significant fractions of light speed. Communication across the galaxy, though slow, is not impossible in principle. The limit sets the rules, but it does not erase the game. We can still imagine journeys, still calculate times, still wonder what it would mean to move through the arms of the Milky Way. That is the power of this boundary. It is absolute, but it also defines the canvas on which imagination can play. To ride beams of light, to send signals, to launch spacecraft, all of it is measured against the same benchmark. The speed limit of the universe may be unbreakable, but it is also the reason our questions have shape. Without it, the galaxy would be unknowable. With it, we can at least measure, even if we cannot reach. When we talk about crossing the galaxy, the first thing we need to know is how large it actually is. It might seem simple enough to say the Milky Way is about 100,000 light-years wide, but that figure hides centuries of difficulty, trial, error, and slow accumulation of knowledge. Measuring the galaxy from inside it is one of the hardest problems in astronomy. We do not have the luxury of stepping outside and taking a photograph from above. Every detail we learn has to come from within, pieced together like trying to map a forest while standing among the trees, with clouds of fog and darkness blocking much of the view. The history of measuring the Milky Way stretches back long before modern science. Ancient cultures noticed the hazy band across the night sky, naming it with stories and myths. To the Greeks, it was milk spilled from the breast of a goddess, giving the galaxy its modern name. To the Chinese, it was the Silver River. In many traditions, it was a path of light, a bridge between worlds, or a river of souls. These descriptions were not measurements, but they reflected a recognition of the Milky Way as something distinct and vast. No one at the time could guess its true scale, but the awareness of its presence has been part of human experience for thousands of years. Serious attempts to measure the galaxy began in the 18th and 19th centuries. One of the first to try was William Herschel, who, with his sister Caroline, conducted detailed star counts. Herschel assumed that if you counted stars in every direction, the regions with more stars must correspond to thicker parts of the galaxy. Using this method, he concluded that the Milky Way was a flattened disk, with the Sun near the centre. He was correct about the disk shape, but his placement of the Sun was off. Dust clouds obscured his view, making star counts unreliable in certain directions. His map was a bold first step but incomplete. Later, in the early 20th century, new techniques changed everything. Astronomer Henrietta Leavitt discovered a relationship between the brightness and period of certain variable stars, known as Cepheid variables. This breakthrough allowed astronomers to measure distances to stars far beyond the reach of parallax, which had been the only reliable method before. By studying Cepheids, astronomers like Harlow Shapley could map the distribution of star clusters and determine the true size of the Milky Way. Shapley found that the galaxy was far larger than previously thought, tens of thousands of light-years across, and that the Sun was not at the centre, but offset, located in one of the spiral arms. This was a profound shift in our understanding, moving humanity from a central position to a more modest one. As technology advanced, so did the accuracy of measurements. Radio astronomy allowed astronomers to look through the dust that blocks visible light. Neutral hydrogen gas emits radiation at a wavelength of 21 centimeters, and by mapping this emission across the sky, astronomers could trace the spiral arms of the galaxy. This gave the first clear evidence of the Milky Way structure as a barred spiral, with arms winding out from the centre. Infrared telescopes added more detail, since infrared light penetrates dust better than visible light. Together, these tools built a picture that is still being refined today. In recent years, the European Space Agency's Gaia mission has revolutionized the process. Launched in 2013, Gaia has measured the positions and motions of more than 1 billion stars with extraordinary precision. These data points form a three-dimensional map of the galaxy, showing not only where stars are but how they are moving. This has allowed astronomers to refine estimates of the galaxy's size, shape and mass, and to uncover features like the warp in the disk and streams of stars left behind by smaller galaxies merging with the Milky Way. Gaia's results confirm that the disk is about 100,000 light-years across, though its halo of dark matter and old stars extends much farther, possibly 200,000 or even 300,000 light-years. Measuring the galaxy is not just about size, it is also about mass. By studying the rotation curve of stars, that is, how fast they orbit the galactic centre at different distances, astronomers discovered that the visible matter alone cannot account for the observed motions. Stars far from the centre move faster than expected, which implies the presence of additional unseen mass. This is the evidence for dark matter, a mysterious substance that does not emit or absorb light but exerts gravity. Estimates suggest that dark matter, makes up the majority of the Milky Way's mass, enveloping it in a vast halo. Without it, the galaxy's rotation would not hold together. So when we measure the Milky Way, we're not only measuring what we see, but what we cannot see as well. These efforts show how much work is hidden behind the simple phrase 100,000 light-years. It is a number built from centuries of observation, from the first star counts to modern space telescopes. Each method has its limits, but together they paint a consistent picture, and yet uncertainties remain. The outer regions of the galaxy are faint and diffuse. The precise extent of the halo is difficult to pin down. Even the number of spiral arms is debated. Some studies suggest 4, others 2 main ones with smaller spurs. The Milky Way is not a tidy object, but a dynamic, evolving system, and measuring it is an ongoing process. For us, though, even approximate numbers are enough to set the scale. When we say the galaxy is 100,000 light-years wide, we're saying that crossing it would take light itself 100,000 years, and any spacecraft much longer. That measurement gives us the framework for all our questions about travel. It tells us what is possible, what is impossible, and what lies in between. It is also a reminder of our place. The Sun lies about 27,000 light-years from the centre, in a small spur between larger arms. That means we are not in a special location. We are not at the core nor at the edge, but somewhere in between, orbiting quietly with billions of other stars. Measuring the galaxy shows us not only its size, but our position within it, a perspective that is both humbling and grounding. Thinking about these measurements also shows us how much effort it takes to understand our surroundings. From Earth's surface, the galaxy appears as nothing more than a glowing band. Only through centuries of work have we come to realize that it is a vast spiral with billions of stars, a central black hole, dark matter, and a history of mergers with smaller galaxies. Measurement is the key that unlocks this understanding, turning a blur in the sky into a structured, knowable place. And this process is not finished. Future missions will refine the map further. New telescopes will look deeper into the halo. Gravitational wave observatories may reveal more about the dark matter that surrounds us. Each new piece of data will add to the picture, sharpening our sense of how large our home really is. For now, though, we can work with the numbers we have, acknowledging the uncertainties but confident in the broad scale. The Milky Way is vast, 100,000 light-years across in its disk, far larger in its halo containing hundreds of billions of stars. To cross it is to take on a distance so immense that even our boldest spacecraft barely scratch its surface. Knowing this, we can now move forward to ask what such a measurement means for the travellers we imagine. With the numbers in hand, we can calculate times, compare speeds, and place ourselves in the story of the galaxy. Measurement gives us the framework. Within that framework, we can explore the possibilities of travel, whether by light, by spacecraft, or by dreams of future technologies. If we let ourselves imagine the ultimate shortcut for travel, it would be to do what light already does. Light is the fastest traveller in the universe, moving at 300,000 kilometers per second, and if there were a way to ride along with it, every journey would be transformed. To hitchhike on a photon is impossible in reality, because photons have no mass and experience no time, but thinking about what it would mean gives us a sense of scale that numbers alone cannot. It allows us to picture the galaxy not as a slow, impossible distance, but as a path light already crosses, constantly and effortlessly. Suppose, just for the sake of thought, that you could shrink yourself down and attach to a photon, leaving a star on one side of the Milky Way. That photon begins its trip across the galaxy and will take 100,000 years to reach the other side. For the photon, the journey is instantaneous. It experiences no time, no aging, no sense of the distance. For you, hitchhiking along, you would feel the full journey only if you reintroduced yourself to time. The strange truth of relativity is that at the speed of light, time ceases to have meaning. That is one reason why no object with mass can ever truly match light's pace. But for imagination's sake, let us set that aside. In the first instant, you would leave your star behind. If you began near our sun, the first 8 minutes would carry you to Earth's orbit. In just over 4 hours, you would have reached Neptune. In 5.5 hours, you would be at Pluto's distance. In a single day, you would have left the solar system entirely, surpassing the distance of Voyager 1, humanity's most distant probe. What takes us decades of effort, light achieves in less than a day. From there, the milestones would come quickly. In a little over 4 years, you would pass Alpha Centauri, the nearest star system. Sirius, the brightest star in Earth's night sky, would come after about 9 years. Stars we know well from constellations would fall behind within decades. The Orion Nebula, where new stars are forming, would pass in a little over 1,000 years. These numbers are large compared to human lifetimes, but small compared to the galaxy itself. Hitchhiking on a photon shows how even the nearest stars, which seem impossibly far with our technology, are crossed with ease by light. But the real test comes when you aim not for nearby stars, but across the entire Milky Way. Even at light speed, the trip requires 100,000 years. That means leaving behind every moment of human history. If a photon set out from one side when the first humans began painting on cave walls, it would still be only partway through the disk today. To finish the journey, it would need to continue on long after our languages, cultures, and possibly even our species have changed beyond recognition. Hitchhiking on a photon forces us to accept the scale of the galaxy, because it shows us that even at the fastest possible speed, the trip is beyond the scope of anything we know. And yet, photons are making this journey all the time. Every star is releasing light in every direction. Billions of photons leave the Milky Way entirely, racing into intergalactic space. Others travel from one arm of the galaxy to another, or from the core outward. Some of them reach Earth, striking our atmosphere, our telescopes, or our eyes. Each photon that arrives carries with it the history of its journey. To hitchhike on one would be to see the galaxy as a series of arrivals, each new place reached in the blink of an eye for light, but in centuries or millennia for us. Astronomers, in a sense, already hitchhike on photons. Every observation they make is based on collecting light that has been travelling for years or longer. When we take an image of a star cluster, we are receiving photons that left those stars hundreds or thousands of years ago. When we image the galactic centre, we are seeing light that began its trip 27,000 years ago. To do astronomy is to wait patiently for photons to arrive, to ride them backwards through time to the place they began. This is the closest we can come to hitchhiking on light in reality, and it is how we know what we know about the Milky Way. If you could ride a photon, you would also experience the galaxy differently in terms of perspective. Distances would collapse. The separation between arms, which spans tens of thousands of light years, would vanish in what feels like an instant. Entire star systems would flash by. From this vantage, the galaxy would seem small, almost compressed, because the limits of time are gone. That contrast with our slow, heavy, massive world is what makes the thought experiment so powerful. It shows us both how vast the galaxy is and how quick light can be. But hitchhiking on a photon also raises questions. If the photon never experiences time, then what would it mean for you to do so? How would you perceive a journey that, from the photon's point of view, does not happen? Relativity tells us that the closer you travel to light speed, the slower time flows for you compared to others. At the exact speed of light, time would stop. For humans bound by mass, this is impossible. The thought experiment breaks the rules, and yet, imagining it allows us to grasp the scale of crossing the galaxy better than any chart or equation. The limits also highlight why light is so central to our understanding of space. Everything we know about galaxies, nebulae, black holes, and stars comes from photons. They are the only carriers of information across the void. To ride one would be to live inside the act of observation itself, to see the universe as it presents itself stripped of delay. In that sense, every time we look at the night sky, we're already participating in the journey. The starlight falling on us has been travelling across the galaxy for millennia. We cannot hitchhike in the literal sense, but we do in the sense that we share in the photon story when it finally arrives. There is also a sobering lesson here. If the fastest possible traveller still takes 100,000 years to cross the Milky Way, then any slower traveller is destined to spend far longer. Hitchhiking on a photon shows us the best case, the lower limit, the absolute boundary of speed. From there, we can only move downward. Our spacecraft may take millions or billions of years. Even speculative engines at fractions of light speed require hundreds of thousands of years. The photon's journey is the cleanest, most direct path, and it shows us why galactic travel is so difficult to imagine for beings who live for less than a century. And yet, the act of imagining it is valuable. It stretches our sense of time. It reminds us that the galaxy is not just a backdrop, but a place full of journeys already happening, carried by light. Photons are crossing the Milky Way constantly. We are surrounded by them, illuminated by them, informed by them. To think of hitchhiking on one is to step into the stream of the cosmos, to see how the fastest traveller makes the impossible journey look routine. When we return from this thought experiment to our own pace, the contrast can feel humbling. But it also gives us a sense of belonging. Even if we cannot ride photons ourselves, we are bathed in their journeys. They reach us from across the galaxy and beyond, and through them we know where we are. They are our messengers, our explorers, our hitchhiking partners, whether we notice them or not. And with them as guides, we can continue thinking about what it would mean for us, bound to mass and limited engines, to move across the Milky Way in our own slower way. When people think of journeys into the wider universe, there are two names that often come to mind before any others: Voyager 1 and Voyager 2. These spacecraft are not fast compared to beams of light, and they are not designed to cross the galaxy, but they hold a special place in our imagination because they represent humanity's first steps into true interstellar space. Looking at the galaxy from the perspective of the Voyagers gives us a sense of scale that is grounded not in theory, but in the real achievements of engineering, patience and persistence. Voyager 1 was launched in September of 1977, followed shortly by Voyager 2, which had actually left Earth earlier but followed a slower trajectory. Their original missions were focused on exploring the outer planets. Voyager 1 flew past Jupiter in 1979 and Saturn in 1980, sending back detailed images and data that transformed our understanding of those worlds. Voyager 2 took a different path, visiting not only Jupiter and Saturn, but also Uranus in 1986 and Neptune in 1989. With these encounters, the Voyagers became the first and only spacecraft to directly study all 4 of the outer giant planets. But their missions did not end there. After completing their planetary flybys, both Voyagers continued outward, carrying instruments still capable of returning data. Voyager 1 is now more than 160 astronomical units from Earth, about 24 billion kilometers away, making it the most distant human-made object. Voyager 2, on a slightly different path, is more than 130 astronomical units away, also well beyond Pluto. Both have passed through the boundary of the heliosphere, the bubble created by the sun's solar wind, and are now travelling through interstellar space. This alone is remarkable. For the first time, humanity has machines that are physically outside the protective bubble of our star, directly sampling the medium between the stars. The speed of Voyager 1 is about 61,000 kilometers per hour relative to the Sun. At that pace, it moves about 17 kilometers every second. This is fast compared to airplanes or rockets, but small compared to galactic scales. To cover a single light year, Voyager 1 would need more than 17,000 years. To cross the galaxy, it would take about 1.5 billion years. From the Voyager's perspective, the galaxy is essentially infinite. It will never reach another star system in any time frame we can reasonably imagine. Its speed is not enough, and its instruments will not last that long. Even so, it continues to drift outward, carrying with it a small piece of Earth's history. That history is stored on the Golden Record. Each Voyager carries a phonograph record made of copper and plated with gold, containing sounds and images from Earth. Greetings in 55 languages, music from different cultures, natural sounds like waves, wind and birdsong, all are etched into the disc. Instructions for how to play it are inscribed as well, along with a map showing the position of the Sun relative to pulsars, so that any finder could trace its origin. The record is not meant as a practical communication tool. The odds of another civilization encountering it are tiny. Instead, it is symbolic, a gesture that says, humanity was here, humanity reached outward, humanity cared to be remembered. From the perspective of the galaxy, the Voyagers are nothing more than grains of dust. They move slowly, they carry almost no mass, and they represent a trivial fraction of the Milky Way's contents. But from our perspective, they are enormous achievements. They are proof that we can build machines that leave Earth, survive for decades, and continue sending information across billions of kilometers. They remind us that exploration is not only about arriving somewhere, but about pushing boundaries no matter how small. The data the Voyagers still return is valuable. Their instruments measure cosmic rays, magnetic fields, and plasma densities in interstellar space. These readings help scientists understand the environment outside the heliosphere, something no spacecraft had ever directly sampled before. Even though the instruments are aging and the power supplies are dwindling, each signal that comes back is another milestone. It shows that even at great distances, human machines can still communicate. The faint radio waves take more than 22 hours to reach Earth, travelling at the speed of light, but they still arrive. Thinking about the galaxy from the Voyager's perspective is humbling. For the spacecraft, every nearby star is unimaginably far away. Alpha Centauri, the nearest star system, is about 4.3 light-years distant. At Voyager 1's speed, it would take more than 70,000 years to get there. That is nearly as long as all of recorded human history, and that is just the nearest star. Most others are far more distant. The Milky Way as a whole is so vast that Voyager's progress barely registers on its scale. And yet, the perspective is important. It shows us how our journey has begun. We may not be crossing the galaxy in any practical sense, but we are reaching into it. The Voyagers represent the first wave of explorers, tiny and fragile but persistent. Their slow march outward is a metaphor for our own growth as a species. Each generation may send probes a little farther, a little faster. One day, the timescales might shrink from billions of years to millions, or even hundreds of thousands. The Voyagers are reminders that progress begins with small steps. It is also worth thinking about what will happen to them. Long after their instruments fail, the spacecraft will continue drifting. Their golden records will survive for hundreds of millions or even billions of years in the cold of space. Long after Earth has changed, perhaps even long after humanity is gone, the Voyagers will still exist, silent but intact, carrying their messages. They will become artifacts of a vanished species, floating endlessly through the galaxy. From that perspective, they are our first attempts at permanence beyond Earth, our first seeds scattered into the cosmic wind. If we place ourselves in the Voyager's position, moving slowly outward into interstellar space, we gain a clearer sense of how vast the Milky Way truly is. The galaxy is not just big, it is so big that our fastest machines will never cross it. Light makes the trip in 100,000 years. Voyager would need 1.5 billion. That ratio is the gap between physics and engineering, between what is allowed and what we can actually do. The Voyagers live in that gap, showing us the reality of the slow march, and yet their perspective is not hopeless. It is inspiring. Every kilometre they cover is a reminder of what is possible. Every faint signal they return is a reminder that distance is not absolute. Even though they are small, they connect us to the larger story of the galaxy. They give us a tangible link to the idea of interstellar travel, however limited. Without them, the concept of leaving the solar system would still be only a dream. With them, it is a fact. When we think of crossing the galaxy, it is easy to become discouraged by the numbers. The timescales are too large, the distance is too great. But from the Voyager's perspective, every bit of progress matters. Each fraction of a light year is a victory. Each image of Jupiter's storms, Saturn's rings, Neptune's winds, and Uranus's moons was once unimaginable. Each piece of data from interstellar space is unprecedented. In that sense, the Voyagers remind us that exploration is not only about completing a journey, but about beginning one. If Voyager 1 shows us that it takes 70,000 years to reach the nearest star at its speed, then what speeds would be needed to shorten that? What technologies could take us beyond? When we look at the scale of our galaxy and realize that even light takes 100,000 years to make the crossing, it becomes obvious that no single human life could ever experience such a journey. Our lives are too short, our civilizations too brief. And yet, the idea of travelling across the galaxy does not die there. Instead, it transforms. It becomes a question not of individual lives, but of generations. What would it mean for an entire lineage of people to live aboard a vessel, passing the torch from parents to children to grandchildren, each generation moving forward without ever seeing the end? This is where the concept of a generation ship emerges. It is one of the most serious proposals for interstellar travel, and though it is still far beyond our current abilities, it provides a way to think about journeys measured in millennia. The idea is straightforward. If a voyage is going to take thousands or tens of thousands of years, then no single crew can complete it. Instead, the crew becomes a society. The ship is built to sustain life indefinitely, with each generation growing up, living and passing on the responsibility to the next. The destination is reached not by the people who set out, but by their descendants. To imagine this, we can start with scale. Let's say a ship could be built that travels at 1/10 the speed of light. At that speed, it would still take 1,000,000 years to cross the Milky Way. Even to reach the nearest star, Alpha Centauri, the trip would take 40 years. That is close enough to fit into a human lifetime, but only barely. For journeys longer than that, the multi-generational model becomes necessary. Imagine aiming not for the full width of the galaxy, but for a star 100 light-years away. At 1/10 light speed, that would take 1,000 years. No person could make that trip. But a society could. Living on such a ship would mean redefining what travel means. For us, travel is about leaving one place and arriving at another. For a generation ship, the voyage itself is the home. People would be born, live their lives, and die without ever setting foot on another planet. Their world would be the interior of the ship. Their landscapes would be corridors, habitats, artificial gardens, and recycled air. The stars outside would move only slightly in their lifetimes. Progress toward the destination would be measured not in personal milestones, but in historical records kept over centuries. This raises questions that go far beyond engineering. How would such a society maintain itself? How would traditions, knowledge, and motivation be passed down? The people who began the journey would know the goal, but after 10 or 20 generations, would the descendants still care? Would the purpose of the trip fade, replaced by the immediate realities of life aboard the ship? Historians have pointed out that human societies on Earth often lose track of long-term projects after just a few generations. Cathedrals took centuries to build, but they were rooted in cultural continuity. Could a starship sustain that kind of focus when the destination lies 1,000 years ahead? One answer is that the journey itself would become the culture. Instead of thinking of themselves as travellers going somewhere, the people aboard might think of the ship as their permanent world. The mission could become a myth, something taught in stories and lessons but not experienced directly. the destination might matter less than the sustainability of the community itself. In that sense, the journey would no longer be a means to an end. It would be the end. The ship would not only be a vehicle, but also a society in motion. The technical requirements for such a ship are staggering. It would need to recycle air, water, and food indefinitely. It would need energy sources that last for millennia, or ways to harvest energy along the way. It would need to be large enough to support a genetically diverse population, perhaps tens of thousands of people to avoid inbreeding and ensure resilience. It would need to shield its inhabitants from radiation, collisions with dust, and psychological strain. In essence, it would need to be a miniature world, carrying with it the complexity of Earth but in a contained, engineered form. Even imagining these challenges brings new perspective to the idea of crossing the galaxy. It shows us that the problem is not only distance and speed, it is continuity. Human beings are not designed to think on timescales of thousands of years. Our institutions struggle to last even centuries. To succeed in a generational journey, we would need not only new technology but new ways of thinking, new systems of governance, and new philosophies about purpose and identity. The galaxy forces us to think beyond ourselves. Examples from history can help us understand what such a journey might feel like. Consider long ocean voyages before the modern era. Sailors on ships crossing the Atlantic in the 15th and 16th centuries often left home never expecting to return. They lived and died at sea, their lives defined by the voyage itself. Or think of isolated communities that have existed for centuries in remote parts of the world, cut off from broader contact. Generations lived in the same valley or island, their culture shaped by the limits of their environment. A generation ship would be similar, except the isolation would be absolute. There would be no outside world to visit, no new supplies, no rescue. The community would be entirely self-sufficient. The psychological impact of this would be profound. People might struggle with the knowledge that they would never see the destination. Motivation might wane, or perhaps the opposite could happen. The very act of being part of a great mission could inspire meaning. Some might find comfort in knowing they are links in a chain, each generation necessary to carry the next closer to the goal. The culture of the ship might develop rituals, stories, and institutions to keep the purpose alive. Over centuries, those traditions might evolve, just as cultures evolve on Earth, until the ship's society barely resembles the one that launched. If we extend this thought to a full galactic crossing, the timescales become staggering. At 1/10 the speed of light, it would take 1,000,000 years. That is not dozens of generations or even thousands, but tens of thousands. Entire species evolve in less time. Civilizations rise and fall in far shorter spans. To imagine a generation ship making that crossing is to imagine not just a journey, but the creation of a new civilization, one that might diverge so much from its origins that by the time it arrives, it would no longer be recognizably human. Language, culture, even biology might change. The descendants who reach the far side of the galaxy might be entirely different from the people who left. This too is part of the perspective the galaxy gives us. When we ask how long it would take to cross, we're not only asking about time, we're asking about transformation. The journey would not leave us unchanged. It would reshape who we are. Generations on a journey would not just be travelers, they would be pioneers of entirely new forms of life and society. Some thinkers have proposed alternatives to human crews for this reason. Instead of sending people, we could send machines that carry the seeds of life, or artificial intelligence that could maintain itself indefinitely. But even if that becomes possible, the idea of a generation ship remains compelling, because it is about continuity. It is about seeing ourselves not as individuals, but as part of a chain that stretches far beyond our lifetimes. In this way, the galaxy challenges us not only technologically, but philosophically. It asks us whether we can think in terms of generations rather than individuals, whether we can sustain purpose across millennia, whether we can redefine success not as arrival, but as perseverance. The answers are not clear, but the questions themselves are valuable. They show us how vast the Milky Way is, and how much it demands from us if we ever hope to cross it. And as we hold this thought, we can see how the concept of generations on a journey connects back to everything else we've considered. Light makes the crossing in 100,000 years. Spacecraft crawl along for billions. Time dilation offers strange possibilities, but never removes the limit. The only way for beings like us to approach the task is to stretch our perspective, to accept that we cannot do it alone, that it would take not just lifetimes, but entire civilizations. Generations would be the currency of such a voyage. When the vastness of the galaxy begins to feel overwhelming, it is natural to wonder whether the universe might allow some kind of shortcut. If light speed is the limit and even a photon needs 100,000 years to make the crossing, then perhaps there is another way. This is where the ideas of warp drives and wormholes enter the discussion. They are not technologies we can build today, and they may never be, but they show how far imagination can stretch when confronted with impossible distances. They also highlight the difference between what the laws of physics say is forbidden and what they leave open as theoretical possibilities. A warp drive, in its most familiar form, is an idea proposed in the 1990s by physicist Miguel Alcubierre. Building on Einstein's equations of general relativity, Alcubierre showed that it was mathematically possible to create a bubble of space-time that contracts in front of a ship and expands behind it. The ship itself would sit inside the bubble, technically motionless relative to the space around it. But because space itself is shifting, the bubble could move faster than light relative to distant observers. This would not violate relativity, because the ship would never locally exceed light speed. Instead, it would be space-time itself that carried the ship forward. The concept is fascinating, but the problems are enormous. To create such a bubble would require vast amounts of energy, possibly more than the mass of the universe converted into usable form. Worse, the bubble requires negative energy or exotic matter, things that have never been observed in sufficient quantities. The mathematics is elegant, but the engineering seems impossible. Still, the idea lingers because it offers a way to imagine effective faster-than-light travel without breaking the rules outright. Wormholes offer a different kind of shortcut. Also rooted in general relativity, they are solutions to Einstein's equations that connect two distant points in space-time through a tunnel. Enter one mouth of the wormhole and emerge instantly from the other, no matter how far apart the two entrances are in ordinary space. The idea dates back to the 1930s, when Einstein and Nathan Rosen first described what became known as the Einstein-Rosen bridge. Later work by John Wheeler and others explored the conditions under which wormholes might exist. Like warp drives, they do not technically break the speed of light limit, because the traveller does not move faster than light through space. Instead, space itself is folded so that the distance is shorter. The challenges here are similar. Wormholes are unstable. To keep one open would also require exotic matter with negative energy density. Without it, the throat of the wormhole would collapse before anything could pass through. Even if they could be stabilized, the practicalities of creating or locating such structures are beyond anything we can imagine. Some theories suggest that tiny wormholes might exist at quantum scales, but none have been observed. As with warp drives, the idea remains theoretical. Even so, the dreams of warp and wormholes persist in both science and culture. They provide a way of thinking about galactic travel that does not rely on millennia-long voyages. In science fiction, they are often used as storytelling devices to allow characters to move quickly between stars. But in physics, they serve as reminders that space-time is flexible. The fabric of the universe is not rigid. It can bend, stretch, and curve. The same equations that explain black holes also allow for warp bubbles and wormholes as mathematical possibilities. Whether nature actually allows them is another question. To appreciate why these ideas are so compelling, it helps to return to the scale of the Milky Way. With light speed as the limit, Even the fastest possible crossing takes 100,000 years. With current spacecraft, it takes billions. Warp and wormholes offer a way out of that trap. They promise travel not limited by distance, but by geometry. If space can be bent, then perhaps the crossing can be made in years instead of millennia. Physicists have explored refinements to Alcubierre's warp drive. Some studies suggest ways to reduce the energy requirements, though even the reduced numbers remain astronomical. Ideas about quantum effects, Casimir energy, and dark energy have been proposed as possible sources, though none are practical with our current knowledge. Wormholes too have been studied in the context of quantum gravity and string theory. In some versions of these theories, wormholes might naturally connect different regions of the universe. Again, none of this has been confirmed, and most of it is speculative. But the fact that the equations allow it keeps the door open, at least mathematically. It is worth noting that warp drives and wormholes are not free of complications even if they were possible. They raise questions about causality, time travel, and paradoxes. A warp bubble could, under some conditions, allow for closed time-like curves, paths through space-time that loop back on themselves, creating the possibility of arriving before you left. Wormholes could also create time travel scenarios if one mouth is accelerated relative to the other. These possibilities are part of why many physicists suspect that nature has mechanisms to prevent such structures from forming or persisting. Stephen Hawking even proposed a chronology protection conjecture, suggesting that the laws of physics forbid time machines. But as long as the equations permit the solutions, the dreams remain. They serve as thought experiments that push the limits of what we can conceive. They remind us that the galaxy is not only vast, but also embedded in a fabric of space-time that is stranger than our daily experience suggests. They also highlight the difference between the impossible and the unknown. Travelling faster than light through space is impossible, but reshaping space itself is in the category of unknown, allowed on paper, but unconfirmed in reality. That distinction matters, because it means that our imagination has room to explore. From the perspective of crossing the galaxy, warp drives and wormholes represent a kind of hope. Not a practical hope, at least not yet, but a conceptual one. They tell us that maybe, just maybe, the laws of physics leave a loophole. Even if the loophole is closed by some deeper theory we do not yet know, the act of looking for it expands our understanding. It forces us to study relativity, quantum mechanics, and cosmology more deeply. It pushes science forward. At the same time, these ideas remind us of the value of imagination. Without imagination, we would never have built telescopes, spacecraft, or probes. Every achievement began as a dream that seemed impossible at the time. Warp drives and wormholes may remain in that category forever, or they may one day inspire real technologies. Either way, they are part of the human response to the vastness of the galaxy. Faced with distances we cannot cross, we invent ways to picture shortcuts, and perhaps that is their most important role. They give us language for thinking about the unthinkable. They let us talk about crossing the Milky Way, not in billions of years, but in moments. They are metaphors as much as hypotheses, helping us grasp the immensity of the galaxy by imagining ways to leap across it. Even if the leaps never come, the act of imagining them brings us closer to the reality of where we are. As we carry these dreams with us, we can return to the practical. Warp and wormholes may remain out of reach, but they frame the problem. They remind us why the galaxy feels so far away, and why even small advances in propulsion matter. They sit at the boundary of science and speculation, lighting the edge of what we can imagine. When people first hear that the galaxy is 100,000 light-years across, the reaction is often disbelief. It is too large, too long, too far beyond anything we know. And then, when they learn that even at the speed of light the journey would take 100,000 years, the idea of crossing the Milky Way seems completely out of reach. But relativity complicates this picture. It introduces a twist that makes the question less straightforward. The closer you travel to the speed of light, the more time slows down for you relative to someone who remains at rest. This is the puzzle of time dilation, and it changes the way we think about journeys across the galaxy. To understand it, it helps to begin with Einstein's theory of special relativity, published in 1905. One of its central claims is that the speed of light is the same for all observers, no matter how they are moving. This has consequences for the way we experience time. If light speed is constant, then time and space must adjust to preserve that constancy. The faster you move, the slower your clock ticks relative to someone standing still. To you, everything seems normal, but to an outside observer, your time stretches. This is not just a thought experiment. It has been measured many times, with high-precision atomic clocks placed on fast-moving planes, satellites, and spacecraft. Each time, the moving clocks tick more slowly, exactly as relativity predicts. Applied to galactic travel, this means that even if the trip seems impossibly long from Earth's perspective, it could seem shorter to the traveller. Suppose a spacecraft could reach 90% of the speed of light. From Earth's point of view, the time to cross the galaxy would still be over 100,000 years. But for the people on board, the time would be less, perhaps only a few tens of thousands of years, depending on the exact speed. Push closer to 99.9% of light speed, and the difference becomes even more extreme. For the travellers, the journey might take only a few centuries or even decades, while for Earth, hundreds of thousands of years would pass. This is the puzzle. The same journey has two different answers, depending on where you measure from. From Earth's perspective, no one can cross the galaxy in a human lifetime. From the traveller's perspective, it might be possible. Both answers are correct within relativity. Time itself is not absolute. It depends on motion. A famous way of illustrating this is the twin paradox. Imagine one twin stays on Earth while the other boards a ship travelling close to light speed. The travelling twin experiences time more slowly. When they return, the Earthbound twin has aged decades or centuries, while the traveller has aged only a few years. This paradox has been tested in small ways with fast-moving particles and clocks. The results match the theory. The twin who travels would indeed return younger. Applied to a galactic crossing, this means the crew of a near-light-speed ship could, in principle, make the trip and feel only a fraction of the time pass, while the rest of humanity would see ages slip by. But relativity does not remove all obstacles. The energy required to reach such speeds is immense. Even accelerating a small mass to 99% of light speed would demand more energy than humanity has ever produced. Collisions with interstellar dust would be catastrophic, and communication between ship and Earth would be complicated by the different flows of time. So while time dilation allows the puzzle of shorter subjective journeys, the practical challenges remain severe. Still, it is worth imagining what such a trip would feel like from the traveller's side. You board a ship designed to accelerate gradually to near-light speeds. As the engines fire and the ship approaches the limit, you feel time inside continue as normal. You eat, sleep, work, and live according to your clock. But when you look outward, strange things happen. Stars ahead appear blue-shifted, compressed toward the front. The sky behind grows red-shifted, stretched into longer wavelengths. Distances seem to shrink. From your point of view, the galaxy is being compressed in the direction of travel. The crossing that should take millennia appears to fit into a shorter span. You live through only a slice of what the rest of the universe experiences. From Earth's perspective, however, your journey is unfolding across the full length of time. People watch your ship recede, centuries pass, civilizations rise and fall, languages change, continents shift. By the time your ship arrives, Earth is unrecognizable. To you, it was a journey of decades. To Earth, it was a journey across epochs. Both are true. The puzzle is not a contradiction, but a feature of relativity. Time is not universal. It depends on who is moving. This dual perspective raises fascinating implications for crossing the galaxy. On one hand, time dilation offers a loophole for the traveller. They could, in principle, reach distant parts of the Milky Way within their lifetime. On the other hand, it severs the connection with the world they left behind. The price of the shortcut is that the rest of humanity moves on without them. The crew becomes exiles in time, separated not only by space but by centuries or millennia of history. When they look back, they see a world that no longer exists. When they arrive, they encounter a galaxy changed by time they did not share. This is why time dilation is a puzzle, not just a curiosity. It reshapes what a journey means. A ship might reach the far side of the galaxy in what feels like 50 years for the crew. But when they arrive, 100,000 years have passed for everyone else. The world they came from is gone. The destination is not only another place but another time. Experiments on Earth help us grasp how real this is. At particle accelerators, unstable particles called muons are created at high speeds. At rest, they decay in millionths of a second. But moving close to light speed, they live much longer, because their internal clocks slow down. We can measure this directly. Their lifetimes stretch in perfect agreement with relativity. The same principle would apply to humans on a starship. Their biological processes would slow relative to Earth, even though they would not notice it themselves. Time dilation also affects communication. Suppose a ship travels at 99% of light speed toward the center of the galaxy. From Earth, signals sent to the ship would take thousands of years to catch up, and the crew's responses would be delayed even more. The flow of information would become meaningless for practical purposes. The crew would be cut off not only physically but temporally. Their timeline would diverge from Earth's in ways that prevent any real connection. Some theorists have even suggested that time dilation could make interstellar colonization possible. If small groups of travelers are willing to leave Earth knowing they will never return to the same world, they could reach distant stars within their subjective lifetimes. From their perspective, the galaxy is compressed. From Earth's perspective, they vanish into time. Colonies founded this way would be disconnected, separated not only by distance but by centuries of history. The Milky Way could be populated this way, but not united. It would become a patchwork of civilizations, each on its own timeline, unable to communicate meaningfully with the others. This possibility shows both the promise and the cost of time dilation. It allows individuals to dream of galactic journeys, but it fractures continuity. The galaxy could be crossed, but at the price of leaving behind everything familiar. It is not a solution that preserves connection. It is a solution that emphasizes separation. And yet, the puzzle continues to fascinate. It shows us how different the universe is from our intuition. We think of time as absolute, the same for everyone. Relativity shows it is not. It bends and stretches with motion. The galaxy reveals this truth on scales too large to ignore. To ask how long it takes to cross is to ask whose clock you're using. The answer is not one number, but two. Both are true, and they do not match. This is why the time dilation puzzle is so central to thinking about the galaxy. It forces us to recognize that travel is not only about distance, but also about time. The moment you begin moving close to light speed, you enter a new frame of reality, one where journeys shrink for you but stretch for everyone else. Crossing the Milky Way is not just a question of speed, it is a question of perspective. Time dilation offers possibilities, but also raises profound challenges. It shows us that the rules of the universe are more flexible than we might think, but also that those rules come with consequences. As we move forward, we carry this puzzle with us, knowing that any attempt to cross the galaxy will be shaped not only by where we go, but by how time itself will treat us along the way. When people imagine travelling across the galaxy, the first obstacles that come to mind are usually distance, time, and speed. But if you think carefully about what lies between one side of the Milky Way and the other, there are other hazards that must be considered. Among the most dramatic are black holes. These strange objects are scattered throughout our galaxy, some small, some massive, some hidden in darkness, and one truly enormous at the very centre. If you were to draw a path across the Milky Way, Sooner or later you would pass near some of them, and their presence would shape the journey. A black hole is a region where gravity is so strong that nothing, not even light, can escape. The idea comes directly from Einstein's general relativity, which shows that mass curves space-time. When enough mass is concentrated into a small volume, the curvature becomes so extreme that it creates a horizon, a boundary beyond which escape is impossible. To an outside observer, this region is invisible. No light comes out. All that can be seen is the influence on nearby stars, gas and dust. In our galaxy, the largest black hole is Sagittarius A, located at the centre, about 27,000 light-years from Earth. It contains about 4 million times the mass of the Sun, packed into a region smaller than our solar system. Its existence was confirmed by tracking the orbits of stars that whip around the centre at incredible speeds, pulled by an unseen mass. The Nobel Prize in Physics in 2020 was awarded for this work. If you were crossing the Milky Way, this central black hole would be one of the most important landmarks, an immense gravitational anchor around which the entire galaxy orbits. But Sagittarius A is not the only one. Stellar mass black holes formed when massive stars collapse at the end of their lives are scattered throughout the disk. Astronomers estimate there may be millions of them in the Milky Way. Most are invisible because they do not emit light unless they are feeding on gas from a companion star. When they do, they produce X-rays and other radiation that allow us to detect them. Otherwise, they are silent, hidden, detectable only by their gravitational effects. This makes them both fascinating and potentially hazardous to any imagined journey. Suppose you were travelling across the galaxy in a ship. The odds of directly colliding with a black hole are vanishingly small because they are not large targets. But passing near one could have dramatic effects. Its gravity could alter your trajectory, slingshotting you onto a different path or pulling you inward to destruction. Even without crossing the event horizon, the tidal forces near a black hole can be immense. Objects stretched too close would be pulled apart in a process sometimes called spaghettification. For a ship or crew, the only safe strategy would be to give wide berth to such regions. Black holes also act as markers of galactic history. Each stellar mass black hole represents a massive star that lived, burned through its fuel, exploded as a supernova, and collapsed. They are fossils of past generations of stars. Along the road across the galaxy, encountering these black holes would be like seeing gravestones, silent reminders of stars that once shone brightly but are now gone, leaving only invisible remnants. There are also intermediate mass black holes, objects heavier than single stars but lighter than supermassive ones. Their existence is harder to confirm, but evidence suggests that some may exist in clusters or dwarf galaxies that orbit the Milky Way. If so, they represent another layer of the landscape. The galaxy is not simply full of stars, it is dotted with these extreme objects, each bending the space around it, each shaping the paths of matter and energy. For travellers, black holes are not only hazards, but also potential tools. Just as Voyager 1 used the gravity of Jupiter and Saturn to gain speed, a ship might in principle use the gravity of a black hole for a slingshot manoeuvre. Approaching at the right angle and distance, the ship could gain velocity from the black hole's immense pull without falling in. This would be extremely dangerous, but in theory, it could shorten a journey. The same gravity that threatens destruction could also offer assistance if handled with precision. From Earth, we study black holes not by visiting them but by observing their effects. The Event Horizon Telescope, a global network of radio telescopes, produced the first direct image of a black hole's shadow in 2019, capturing the supermassive black hole at the centre of the galaxy M87. In 2022, the same technique was used to image Sagittarius A. These observations confirm that black holes are not just theoretical but real, with visible signatures of their horizons and accretion disks. Knowing they exist, and where they are, is crucial to mapping any imagined crossing of the galaxy. Black holes also contribute to the larger puzzle of time. Near the event horizon, time slows dramatically relative to distant observers. A clock near a black hole ticks more slowly. This effect is extreme only very close to the horizon, but it reinforces the idea that black holes are not just physical objects but distortions of space and time. Travelling near one would not only alter your path, but also your experience of duration. Some black holes are paired with stars, forming systems where gas from the star is pulled into the black hole. As the gas spirals inward, it heats to millions of degrees and emits powerful X-rays. Observations of these systems help astronomers estimate the number and distribution of black holes in the galaxy. Others may roam alone, invisible except for their gravitational pull. Surveys suggest there could be around 100 million stellar mass black holes in the Milky Way. The chance of encountering one on a straight path is tiny, but their sheer number ensures that any crossing would pass relatively near several of them. Imagining black holes along the road gives the galaxy texture. It is not an empty void, but a landscape dotted with extremes. Stars, nebulae and clusters define much of the scenery, but black holes add both danger and mystery. They remind us that the galaxy is a place of creation and destruction, where massive stars live fast and die violently, leaving behind these invisible remnants. They also remind us that the rules of physics grow stranger the closer you get to them, blending gravity, time and space into something we still do not fully understand. For a traveller, planning a course would mean not only calculating distances and speeds, but also mapping where the hazards lie. Just as ancient sailors studied charts to avoid reefs and storms, interstellar navigators would need to mark the positions of black holes, staying far enough away to avoid their pull, yet aware that their presence cannot be ignored. Some might even choose to swing close to them for a boost, though that would require extraordinary precision. Either way, the journey would be shaped not just by empty distances, but by encounters with these silent giants. Thinking of black holes along the road also helps us appreciate the galaxy from where we stand. We cannot cross the Milky Way, we cannot even send ships to the nearest star, but we can detect black holes thousands of light years away, measure their masses, track their orbits, and even image their shadows. That ability connects us to the broader galaxy, reminding us that even the most extreme objects are within our reach in terms of knowledge, if not travel. And as we hold this in mind, we can see how black holes fit into the broader question of crossing the galaxy. They are part of the environment, part of the hazards and opportunities, part of the map we would need to draw. They make the journey more complex but also more real. The galaxy is not a smooth disk waiting to be crossed. It is a dynamic system filled with stars, gas, dark matter and black holes. To imagine travelling across it, we must imagine passing near all of these things, each shaping the road in its own way. If you imagine trying to cross the Milky Way, one of the first questions that arises is how you would know where to go. The galaxy is not a simple stretch of road with signs along the way. It is an ocean of stars, hundreds of billions of them, each shining with its own light, each positioned at some unique distance and angle. In that sense, the only map available to any traveller is the light those stars send out. Every photon that reaches us is not only illumination, but also information. To learn how to read that information is to learn how to navigate, and to realise that starlight itself is the guidebook for crossing the galaxy. On Earth, navigation has always relied on light. Before compasses, before GPS, sailors steered their ships by the sun during the day and the stars at night. The constellations were not just patterns in the sky, but tools for orientation. Polaris, the North Star, held its place almost fixed above the horizon, a reliable marker of direction. Entire voyages were undertaken across oceans using little more than starlight and skill. The same principle applies to the galaxy, only on a much larger scale. Stars serve as markers of position, their light carrying clues about where we are and where we're going. The key lies in the fact that starlight is not uniform. Every star has its own spectrum, a fingerprint of lines that reveals its composition, temperature and motion. When light from a star is spread into a spectrum, dark lines appear where atoms absorb specific wavelengths. By studying those lines, astronomers can identify the elements present. More importantly, the lines shift depending on motion. If a star is moving toward us, its light is slightly compressed, shifting toward the blue. If it is moving away, the lines shift toward the red. This Doppler effect allows astronomers to measure velocities with great precision. In this way, starlight becomes a record not only of what a star is, but also of how it moves. Distances, too, can be drawn from light. Nearby stars can be measured using parallax, the tiny shift in their apparent position, as Earth orbits the Sun. For more distant stars, astronomers use standard candles, objects whose intrinsic brightness is known. Cepheid variables, with their predictable relationship between brightness and pulsation, are prime examples. By comparing how bright they appear to how bright they should be, astronomers calculate their distances. Starlight, in other words, contains the ruler as well as the compass. It tells us both direction and distance, turning the sky into a three-dimensional map. This is how the shape of the Milky Way has been uncovered. By collecting light from countless stars, astronomers piece together their positions and motions, revealing spiral arms, clusters, and the central bulge. Gaia, the European Space Agency's mission, has taken this to extraordinary levels, measuring the positions and movements of more than 1 billion stars with incredible accuracy. Its data form a living map of the galaxy, showing not only where stars are now, but where they are moving in the future. This is exactly the kind of map any traveller would need. If you were aboard a ship trying to cross the galaxy, you would have no signs, no roads, and no landmarks except starlight. But that would be enough. By measuring the spectra, brightness, and positions of stars around you, you could triangulate your place. The stars themselves are the coordinates. Each photon carries the data needed to find your way. This is what makes starlight such a powerful guide. It is not just beauty, it is navigation written into the universe. The usefulness of starlight extends beyond visible light. Infrared, ultraviolet, radio, and X-rays all carry additional information. Infrared penetrates dust, revealing stars hidden from view. Radio waves trace cold gas, showing the arms of the galaxy. X-rays point to extreme objects like neutron stars and black holes. Each wavelength is a different layer of the map. Together they form a multi-dimensional atlas of the Milky Way. A traveller who could read across the spectrum would have a far richer sense of position than one limited to visible light alone. It is worth remembering how much of this knowledge comes from Earth already. Astronomers have mapped the motions of stars near the galactic centre, tracked the rotation curve of the disk, and measured the halo of dark matter, all from the analysis of starlight. We have never left the solar system with crewed ships, yet we already know the structure of the galaxy in broad terms. That knowledge comes entirely from photons. If we ever do attempt journeys across the Milky Way, the groundwork is already here. For a traveller, the challenge would be scale. On Earth, sailors navigating by stars could measure changes in position over days or weeks. In the galaxy, changes in position relative to distant stars would be subtle over a lifetime. A ship might move for centuries before its motion relative to background stars became obvious. But with precise instruments, those shifts could be measured. The same way Gaia tracks parallax from Earth, a ship could track parallax from its own motion. Over time, the accumulated data would reveal the path. Starlight can also serve as a clock. Pulsars, the rapidly rotating remnants of massive stars, emit beams of radiation at regular intervals. These pulses are so precise that they rival atomic clocks. A network of pulsars could function as a galactic GPS, allowing ships to locate themselves anywhere in the Milky Way by measuring the timing of the signals. This idea is already being tested for spacecraft navigation within the solar system. In the context of a galactic journey, it would be indispensable. The galaxy provides its own beacons. All we have to do is learn to read them. Of course, relying on starlight has limitations. Dust clouds obscure large parts of the galaxy, blocking visible light. Extinction dims stars, making them appear farther than they are. Variability in stars can complicate measurements, but each of these challenges has solutions. Infrared and radio bypass dust. Statistical methods correct for extinction. Careful observation over time accounts for variability. Starlight is not perfect, but it is abundant, and its abundance makes it reliable. Thinking of starlight as a map also reshapes how we think of the journey itself. It reminds us that the galaxy is not a void, but a field of markers. Each star is a point on the chart. Each cluster is a landmark. Even the dark gaps where few stars shine are information. They tell us where the dust is thickest, where the arms are sparse. The map is not only the light we see, but also the shadows where light is missing. And this perspective has a comforting implication. Even if we never build ships that cross the Milky Way, we already share in the act of navigation. Every telescope pointed at the sky is reading starlight, plotting our place, charting our surroundings. We may not move across the galaxy physically, but we map it constantly through photons. In that sense, we're already travellers of light, guided by the stars themselves. For those who dream of galactic journeys, this is an essential lesson. The first step is not speed. The first step is orientation, knowing where you are, where you're going, and how to tell the difference. Starlight provides that foundation. It is the map drawn not by human hands, but by the universe itself, available to anyone who can read its code. And with that, the road across the Milky Way becomes less abstract. It is no longer an empty stretch of time and space. It is a route with markers, signposts and coordinates, all written in light. Whether we ever travel it with ships or not, we already hold the map. The galaxy has drawn it for us, and every night when we look up, we are reading it. When we look up at the Milky Way on a clear night, we often think of it as crowded. The band of light across the sky gives the impression of stars packed together, a glowing ribbon of countless suns, but the reality is very different. For every star we see, there are vast stretches of emptiness between them. If you were travelling across the galaxy, this emptiness would be what you encountered most of the time. The stars themselves would be rare, scattered islands in a sea of space. Between them stretches the silence, an environment so empty that words like desert or void hardly capture it. The average distance between stars in our part of the Milky Way is about 4 light years. That means that if you set out from the Sun and travelled in a straight line, you would, on average, need to go 4 light years before you came close to another star like it. Light covers that distance in 4 years. Voyager 1, our most distant spacecraft, moving at more than 61,000 kilometers per hour, would need over 70,000 years. For a human traveller, the gap between stars is a barrier as daunting as the galaxy itself. What makes the silence between stars so striking is not just the physical emptiness, but the absence of signals. The universe is filled with background radiation, the afterglow of the Big Bang, the faint hiss of energy left over from the birth of the cosmos. But the kind of signals we associate with life, with civilization, are missing. Radio telescopes scan the sky, searching for artificial transmissions, but so far none have been confirmed. The galaxy is not only empty of matter between stars, it is also empty of voices. The silence is literal. For travellers, this silence would be a constant companion. Imagine a ship moving through interstellar space. The stars would be distant points of light, but most of the view would be darkness. The radio receivers would pick up cosmic noise but no messages. Communication with Earth, if possible at all, would take years or centuries depending on the distance. Each step forward would take the ship deeper into isolation. The silence would be more than a lack of sound. It would be the absence of contact, the absence of reassurance that anyone else is near. This reality is why the search for extraterrestrial intelligence is so compelling. If another civilization were transmitting signals, even faint ones, it would break the silence. It would prove that the spaces between stars are not empty of meaning, but so far the search has found nothing. The signals we detect are all natural: pulsars, quasars, interstellar gas. The silence remains. For now at least, the galaxy feels vast and quiet. The emptiness between stars is not absolute. There are particles drifting in interstellar space, mostly hydrogen atoms. There are occasional clouds of gas and dust, some of them dense enough to form new stars. There are cosmic rays, high-energy particles zipping through space. But compared to the density of matter on Earth, the interstellar medium is close to nothing. A cubic centimetre of air at sea level contains about 10 billion trillion molecules. A cubic centimetre of interstellar space may contain just one atom. Travelling through it would feel like passing through a vacuum, because that is essentially what it is. And yet, this near vacuum is not irrelevant. Over thousands of years, the sparse atoms of the interstellar medium would still exert a drag on a fast-moving ship. Dust grains, though tiny, would strike with enormous energy at near-light speeds, creating dangerous impacts. Shielding would be necessary, not because space is crowded, but because even rare collisions at high velocity are catastrophic. The silence is not safe. It hides risks that are invisible but real. From another perspective, the silence between stars is also an opportunity. It is what makes the stars themselves so distinct. In the middle of emptiness, each star becomes a beacon, its light standing out against the dark. The contrast between the silence and the signal is what allows navigation, what makes it possible to use starlight as a map. Without the silence, the signals would blur together. The emptiness gives structure to the galaxy, separating the islands of light so that they can be seen, studied, and understood. The silence also forces us to think about time differently. On Earth, we are used to short communication delays. A phone call or a radio transmission travels instantly for all practical purposes. Even communication with the Moon has only a 1.3-second delay. With Mars, signals take between 4 and 24 minutes, but with the stars, the delays stretch into years. A message sent to Alpha Centauri would take 4.3 years to arrive, and another 4.3 years for the reply. That is nearly a decade for a single exchange. Across the galaxy, the silence becomes permanent. Messages take tens of thousands of years to cross from one side to the other. For practical purposes, there is no conversation possible. The silence is baked into the structure of space-time. From the point of view of a traveller, the silence would shape psychology as much as physics. On Earth, we are rarely truly isolated. Even in remote places, we know that other people are somewhere nearby, that communication is possible. On a journey between stars, that reassurance would vanish. Each passing year would carry the ship farther from Earth's reach. Eventually, the silence would be absolute. The crew would be alone, surrounded only by the faint hiss of background radiation and the distant points of starlight. The mental adjustment required to live with such silence would be profound. Astronomers sometimes describe the galaxy as a desert, and in many ways the metaphor fits. The stars are like oases, scattered far apart with stretches of emptiness between. But deserts on Earth are still full of life. The spaces between stars, as far as we know, are not. They are not home to plants, animals, or civilizations. They are dark, cold, and silent. For any journey across the Milky Way, most of the time would be spent not near stars, but in this silence. The destinations may be bright, but the road is quiet. This silence is also what makes discoveries like pulsars and quasars so striking. When Jocelyn Bell Burnell first detected regular radio pulses in 1967, she briefly wondered if they might be signals from extraterrestrials. The signal was so precise, so unlike the background noise, that it stood out immediately. Later, it was identified as a rotating neutron star, a natural phenomenon. But the moment of wonder was telling. In a universe of silence, any signal that breaks the pattern is extraordinary. The same principle applies to the search for life today. If the silence were ever broken by an artificial signal, it would be the most important discovery in human history. For now, though, the silence holds. The spaces between stars remain empty of voices, filled only with faint radiation and scattered atoms. For a traveller, that silence would be the defining feature of the journey. It would shape the environment, the experience, and the sense of scale. The galaxy may be full of stars, but it is even fuller of space. The road across it is not crowded. It is wide, empty, and quiet. The silence does not mean absence of meaning, it means room for meaning. It means that when signals do arrive, they matter. It means that when stars appear, they shine all the brighter against the void. The silence is not an obstacle to crossing the galaxy, but the medium through which the crossing takes place. To understand the Milky Way, we must understand not only the stars, but also the spaces between them. The long stretches where nothing speaks and nothing moves except at the slow pace of drifting atoms. When we think about journeys, we usually measure them in times that fit within our lives. A walk across a city might take an hour. A drive across a country might take days. A flight around the world can be done in less than 2 days. Even the longest human journeys, such as ocean voyages before modern technology, took months, or at most a few years. Our sense of distance and time is built around scales that fit into a human lifetime. The Milky Way does not fit into those scales. The galaxy forces us to stretch our perspective until it almost breaks, because the simple truth is that crossing it takes forever compared to anything we know. Start with the speed of light. Nothing moves faster. It is the limit set by the universe itself. At that speed, a crossing from one side of the disk to the other still takes 100,000 years. That figure alone is beyond anything familiar. 10 human lifetimes, strung together back to back, reach only about 1,000 years. 100 lifetimes make 10,000 years. To span 100,000 years would require a chain of 1,000 lifetimes. Even if each generation carefully passed on the memory of the journey, the span is so long that the connection would almost certainly be lost. Whole civilizations rise and fall in much shorter times. Languages change, religions shift, nations vanish. 100,000 years ago, humans were still sharing the planet with other hominin species. To cross the galaxy at light speed would require surviving a timescale longer than all of recorded history. Now slow down to the speeds we can actually achieve. Voyager 1, the fastest probe travelling away from Earth, would need 1.5 billion years to cross the galaxy. That is about 1/3 the age of Earth itself. The Parker Solar Probe, though faster in its orbital dives, would still need more than 600 million years if aimed across the disk. These are times so long they erase any hope of continuity. No civilization could realistically maintain a project across such spans. Entire species could evolve, change, and disappear in the time it would take a spacecraft to make the trip. Even more ambitious proposals like ships powered by nuclear fusion or antimatter, which might in theory reach 10 or 20% of the speed of light, still yield enormous times. At 1/10 light speed, the crossing would take 1 million years. At 1/5, it would take 500,000. At half the speed of light, it would still require 200,000 years. The numbers never shrink into manageable scales. They remain stubbornly vast. Why does it take so long? Part of the answer is simple geometry. The galaxy is wide. Its disk stretches 100,000 light-years across, with a thickness of a few thousand light-years. To move from one end to the other is to move across distances so great that even light itself appears sluggish. Another part of the answer is human limitation. We cannot move at light speed. We cannot even approach it closely. Our engines are too weak, our energy reserves too small, and even if we could build faster ships, the risks of collisions, radiation, and resource depletion grow with velocity. The faster you go, the harder the journey becomes. Acceleration is another factor. To reach near-light speeds, you cannot simply press a button. A ship with mass must accelerate gradually. The energy required increases as velocity increases, and slowing down at the destination requires equal effort. any real ship would spend long stretches just speeding up and slowing down. The idealized picture of instantly reaching a constant high speed is not realistic. The physics of acceleration stretches the journey further. There is also the issue of endurance. No known machine lasts for hundreds of thousands of years. Metals corrode, electronics fail, power sources decay. Even if a ship could be launched with near-light propulsion, keeping it functioning for the entire crossing is a challenge that dwarfs any engineering we know. Shielding it from cosmic rays, micrometeoroids, and gravitational perturbations adds more layers of difficulty. Each problem compounds, making the crossing seem not just long, but effectively infinite. And then there is the human factor. Humans live for less than a century. Even extending lifespans with medicine would not bridge the gap to thousands of years, let alone millions. To carry people across the galaxy, you would need generation after generation, or some form of suspended animation, or perhaps the transfer of consciousness into machines. Each of these ideas introduces its own complications, but the underlying problem remains the same. The galaxy is too large for individuals to comprehend as a journey. To us, it takes forever, because forever is the only word that captures time so far beyond experience. Thinking about why it takes forever also highlights the difference between local and galactic scales. Within our solar system, the distances are immense compared to earthly journeys, but manageable compared to the galaxy. Light takes just over 8 minutes to reach Earth from the Sun, and a few hours to reach Pluto. These are delays we can work with. Probes can send data. Signals can be received. Even Mars with delays of minutes can be explored with rovers controlled from Earth. But scale that up to the stars and everything breaks down. Years replace minutes, millennia replace hours. The Milky Way simply operates on scales far beyond the solar system, and that is why every attempt to cross it falls into the category of forever. Time dilation complicates the picture but does not erase it. Yes, from the perspective of a traveller moving close to light speed, the journey may seem shorter. A crew might experience only decades while centuries or millennia pass outside. But that does not reduce the objective timescale of the crossing. For the galaxy as a whole, it still takes 100,000 years at best. Time dilation does not eliminate the forever. It simply divides it into different perspectives. From Earth, the crossing remains unreachably long. From the traveller, it becomes possible but at the cost of disconnecting from everything left behind. The silence between stars contributes as well. Even if a ship could move fast enough, communication lags grow unbearable. A message to Earth from halfway across the galaxy would take 50,000 years to arrive. The crossing is not just long in time, it is long in isolation. Each step forward increases the separation until there is no hope of contact. That isolation reinforces the sense of forever. It is not just a question of when you arrive, but of how long you are alone on the way. And then there are hazards. Black holes, neutron stars, supernovae, and dense molecular clouds all occupy parts of the disk. Travelling across the galaxy would mean encountering or avoiding these dangers. Each requires detours, slowing the journey further. The galaxy is not a straight path. It is a landscape filled with obstacles, each one stretching the forever a little longer. When astronomers calculate these timescales, they are not exaggerating. The Milky Way is what it is, a disk of stars, gas, dust and dark matter, 100,000 light-years wide, rotating once every 230 million years. These are numbers rooted in observation, measurement and physics. The reason crossing takes forever is that forever is the scale of the galaxy itself. The numbers are honest, the difficulty is real, but in another sense forever does not mean impossible. Light makes the trip constantly. Photons leave stars, cross the disk and reach other stars or even other galaxies. Gravity binds the stars together across these immense spans. The galaxy functions as a whole even though its components are so far apart. Forever is a human word rooted in our own brief lifetimes. For the galaxy, 100,000 years is not forever. It is simply a moment. Stars live for billions of years. black holes persist for trillions. From their perspective, the crossing is long but not infinite. This contrast is part of why the question is so captivating. To us, it takes forever. To the galaxy, it does not. The Milky Way operates on timescales we can barely imagine, and placing ourselves against that background forces us to confront our own scale. Our lives are short, our civilizations are young, our technologies are primitive compared to what would be needed. That is why crossing feels unreachable. It is not that the journey is infinite, it is that we are finite. And this understanding leads naturally into other questions. If crossing takes forever, then perhaps the focus should not be on crossing at all, but on learning, mapping, and understanding. Perhaps our role is not to move across the galaxy in ships, but to read it through starlight, to model it with telescopes, to imagine it through theory. Perhaps the galaxy is not meant to be crossed in our terms, but to be comprehended in its own. When the scale of the Milky Way feels overwhelming, it is natural to wonder if there might be a way to cheat. If light itself requires 100,000 years to make the crossing, if spacecraft crawl for billions of years, and if even the boldest ideas of fusion or antimatter engines still yield hundreds of thousands of years, then the mind begins searching for a shortcut. Humanity has always done this. Faced with a mountain, we look for a pass. Faced with an ocean, we look for currents. Faced with the galaxy, we begin to imagine routes that bend or fold space itself, routes that might take us where speed cannot. The most famous shortcut is the wormhole. General relativity allows for solutions in which two distant points in space-time are connected by a tunnel. Enter one end, emerge at the other, skipping the intervening distance. The idea is often illustrated by folding a sheet of paper so that 2 points touch, then poking a hole between them. To cross the paper normally requires moving along its surface. To cross through the hole requires almost no distance at all. Applied to the galaxy, a wormhole could reduce a journey of 100,000 light-years to a single step. The mathematics for wormholes is straightforward enough, but the physical reality is another matter. Wormholes, if they exist, would be unstable. They would collapse before anything could pass through, unless they were held open by exotic matter with negative energy density. No such matter has been found in usable amounts. Even if it exists, controlling it on galactic scales would require technology far beyond anything we can imagine. Still, the possibility remains in theory, and that makes wormholes the archetypal galactic shortcut. They represent the hope that distance is not absolute, that geometry itself can provide an escape from forever. Another imagined shortcut is the warp drive. Instead of moving through space faster than light, the ship manipulates space around it, contracting the region ahead and expanding the region behind. The ship remains motionless inside a bubble of normal space, but the bubble itself moves. This idea, first proposed by Miguel Alcubierre in the 1990s, shows that general relativity permits such a distortion. The problem once again is energy. The amount required is astronomical, far beyond what stars themselves produce, and it requires exotic forms of matter not known to exist. But as a shortcut, it illustrates another path, not through a tunnel, but through manipulation of the medium itself. Beyond these, there are other speculative ideas. Some involve using the fabric of space in ways we do not yet understand. Theoretical models of the universe suggest that extra dimensions may exist, curled up beyond our perception. If those dimensions could be accessed, they might allow shortcuts through higher dimensional space, making galactic distances irrelevant. Others propose that the universe itself may contain cosmic strings, narrow filaments of immense density formed in the early cosmos. Travelling near one could, in theory, alter paths through space-time dramatically. None of these are confirmed. They remain speculative, but they show how imagination stretches when faced with impossible journeys. There are also more practical-seeming shortcuts, though still beyond our current reach. One involves using black holes not as hazards, but as gateways. Some versions of relativity suggest that rotating black holes, known as Kerr black holes, could connect to other regions of space-time. Whether such connections could be traversed is unknown. Another suggestion is to use the energy of stars themselves to power immense solar sails, accelerating ships to high fractions of light speed. This is not a shortcut in space, but a shortcut in time compared to chemical rockets. It does not bend space, but it compresses the journey by using resources already available in the galaxy. When we talk about shortcuts, it is easy to dismiss them as science fiction, and in many cases they are. But science fiction has often served as a testing ground for ideas that later became real. Submarines, airplanes, and rockets were all once considered fantastical. That does not mean wormholes or warp drives will ever exist, but it does mean that imagining them has value. It pushes our understanding of physics. It frames the questions we ask. It highlights the difference between what is forbidden by the laws of nature and what is simply beyond our current technology. Part of the appeal of shortcuts is psychological. When faced with numbers like 1 million years or 1 billion years, the human mind recoils. Those timescales are too vast to process. A shortcut offers relief. It says, perhaps there is another way, a hidden path that makes the impossible manageable. This is not just a desire for convenience, it is a desire for hope. The galaxy feels unreachable. Shortcuts allow us to imagine that it might not be. At the same time, imagining shortcuts helps us understand the structure of the galaxy more deeply. Thinking about wormholes leads to studies of space-time geometry. Thinking about warp drives leads to questions about energy and negative mass. Thinking about higher dimensions leads to explorations in string theory and quantum gravity. Each shortcut, even if never realized, opens a line of inquiry that enriches science. In this way, shortcuts are not escapes from knowledge, but tools for gaining it. It is also worth noting that nature itself provides shortcuts of a kind. Gravitational slingshots, for example, are real. Voyager 1 gained speed by passing near Jupiter and Saturn, stealing a fraction of their orbital momentum. This technique is used by many spacecraft to save fuel and shorten journeys. On larger scales, galaxies themselves act as gravitational lenses, bending light from objects behind them. The principle is the same. Gravity alters paths, creating shortcuts in the way signals or spacecraft move. These are not wormholes, but they are reminders that the universe already provides tools for bending trajectories. If a civilization were advanced enough, it might discover ways to use such effects deliberately. Perhaps stars could be arranged or manipulated to form gravitational highways. Perhaps black holes could be harnessed as gateways. Perhaps energy sources unknown to us could stabilize wormholes or warp bubbles. These are distant ideas, but they give us ways to think about what might be possible in a galaxy where time feels endless. Imagining shortcuts also reveals something about ourselves. It shows that we are not content with limits. We recognize them, respect them, but also test them. The speed of a light is absolute, but that has not stopped us from looking for ways around it. Distances are enormous, but that has not stopped us from asking if space itself could bend. The fact that we dream of shortcuts shows that the galaxy has already succeeded in its greatest effect, making us think beyond our boundaries. From a practical standpoint, we may never find or build these shortcuts, but imagining them is not wasted effort. It helps us see the problem clearly. It helps us appreciate the scale of what we are facing, and it provides a contrast to the slower methods we can actually pursue. By holding both in mind, the dream of shortcuts and the reality of slow journeys, we get a fuller picture of what the galaxy means. And so, when we talk about crossing the Milky Way, shortcuts are always part of the conversation. They are the paths we wish existed, the tunnels and folds we hope might be real. They are not yet ours, but they shape the way we think. And even if we never find them, the act of imagining them brings us closer to understanding what it would mean to move across a galaxy where distance itself seems unending. After following the scale of the Milky Way across distances and times that strain the imagination, it helps to pause and return to the one place we actually know. All of the calculations, the questions about speed, the speculations about shortcuts, and the visions of future ships begin from a single reference point. That point is here, orbiting an ordinary star in one of the spiral arms, in a small system that has, for us, become the entire stage of history. The galaxy is immense, but our perspective begins at home, and it is worth remembering that before imagining the road outward. The Sun lies about 27,000 light-years from the centre of the Milky Way, positioned in a quiet spur between two larger arms, the Sagittarius and Perseus arms. It is not near the dense star clusters of the core, nor on the thin edges of the disk. It is in the middle ground, where stars are spaced at comfortable distances, where orbits are stable, and where conditions allow for planets like Earth. This location is sometimes described as the galactic habitable zone, not too close to the dangers of supernovae in the crowded regions, not too far into the barren outer disk where heavy elements are scarce. For our purposes, it is simply where we find ourselves. Looking outward from here, the Milky Way appears as a band because we are seeing the dense disk from inside it. Looking inward toward Sagittarius, we see the brighter, more crowded regions. Looking outward toward Orion and Perseus, we see fewer stars but still enough to trace the spiral. Every direction shows light, but it is filtered through gas, dust, and distance. We cannot see the whole from where we are, but we can infer it. That is how we know the scale of the journey we have been imagining. From this position, the dream of crossing the galaxy may seem distant, but the act of understanding it is already remarkable. Without leaving home, without travelling even beyond the solar system, humanity has measured the distances to stars, mapped the arms of the disk, detected black holes at the centre, and traced the halo of dark matter that surrounds everything. All of this knowledge has been gathered by studying light that arrives here, on Earth. In that sense, the journey across the Milky Way has already begun, not physically, but intellectually. We are travellers of knowledge long before we are travellers of distance. That perspective also reminds us why the galaxy feels so large. We measure it from our scale, from lives that last less than a century, from civilizations that rarely endure more than a few thousand years. Against that backdrop, 100,000 years at light speed looks impossible. Billions of years at spacecraft speeds look like forever. But from the perspective of stars, which burn for billions of years, or black holes, which can last far longer, the galaxy is not so vast. The journey is only long because we are small. That realization does not make the road shorter, but it does help us understand why it feels endless. Back at home, the questions become more practical. Instead of asking how to cross the galaxy, we can ask how to explore nearby stars, how to send probes to the closest systems, how to build telescopes that reveal more detail. Each of these steps is achievable on human timescales. The scale of the galaxy remains what it is, but the scale of our ambition can adjust. We do not need to span 100,000 light-years to begin. We only need to extend beyond what we have already done. The voyagers are already part of that extension. They are not crossing the galaxy, but they are leaving the solar system, moving slowly outward into interstellar space. Their journeys remind us that every step counts, even small ones. The next steps may be faster probes, sails pushed by light, or swarms of small craft launched toward nearby stars. Each effort brings the galaxy into sharper focus, even if the crossing remains beyond reach. From here, at home, we can measure, plan, and imagine. And perhaps that is the real role of the home in the context of the galaxy. It is the place where imagination begins. The Milky Way is vast, but it is not unknowable. The more we observe, the more the details emerge. Structures once invisible become mapped. Processes once mysterious become explained. What was once only a glowing band in the sky becomes a dynamic spiral with billions of suns. And through that knowledge, the galaxy becomes less an abstraction and more a place we belong to, even if we never cross it. If the galaxy is a road that takes forever, then home is the mile marker that makes the road comprehensible. Without a starting point, distance has no meaning. The Sun and Earth provide that point. Every light year measured, every estimate of galactic size, every discussion of shortcuts or time dilation, all of it begins with the realization that we are somewhere specific. The galaxy is not just a background, it is an environment, and we occupy a position within it. This return to home also highlights the contrast between the vastness out there and the familiarity here. The galaxy is filled with hazards, black holes, radiation, supernovae, but Earth is stable enough for life to persist. The galaxy stretches across unimaginable distances, but Earth fits into the scale of a human life. That contrast does not diminish the galaxy. It makes it more meaningful. It shows that in the middle of immensity, small worlds can exist where life flourishes, where thought arises, where questions about journeys across the galaxy can even be asked. As we imagine crossing the Milky Way, it is easy to feel insignificant. Our ships are too slow, our lifetime's too short. But returning to home reveals the opposite. It is precisely because we are small and brief that the galaxy feels so large. The fact that we can even measure it, describe it, and imagine travelling across it is extraordinary. From this small planet, we have already reached outward in ways that would have seemed impossible to our ancestors. The road may be endless, but the act of seeing it is itself a journey. And so the crossing of the galaxy remains a dream, but one rooted in real knowledge. Each telescope, each probe, each calculation adds to the map. Each new discovery adds to the story. Even if the physical journey takes forever, the intellectual journey continues every day here at home. That journey is what makes the galaxy real to us, and it is the journey that will carry us forward as long as questions remain. Thank you for spending this time with me, drifting through thoughts of stars, distances, and journeys too vast to finish in a single lifetime. I hope it brought you a little calm, a little wonder, and maybe even a sense of how remarkable it is to simply be here, able to imagine it all. If you found this soothing, you can stay connected by liking this video, subscribing to the channel, and turning on the little bell so you'll know when the next quiet exploration begins. And now, as you settle in, you don't need to hold on to the details. You can let them drift away like starlight fading into the dark, knowing they'll still be here when you want to return. All that's left for you to do is rest, safe under your own sky, with the thought of the Milky Way above you, steady and timeless. Sleep well, and good night.